In the vast ocean of the universe, where galaxies dance across the cosmic stage in endless spirals and chaotic collisions, there exists a class of galaxies that defy ordinary perception. They do not blaze with twisted arms like spirals, nor do they shimmer in symmetrical glows like ellipticals. Instead, they whisper secrets of violent pasts and hidden interactions. They shimmer faintly in elliptical halos, surrounded not by stars and orderly formations, but by arcs, ethereal, concentric ripples, like echoes in water after a stone has vanished into the deep. These are shell galaxies, haunting and graceful cosmic apparitions that seem to exist between the real and the surreal. But before we continue, subscribe to the channel so you don't miss out on any of these videos. At first glance, shell galaxies appear to be merely ellipticals or lenticulars, smooth, featureless, and unassuming. But look closer, with the right telescope, and you will see an almost ghostly pattern, vast arcs of starlight forming concentric shells, loops, or ripples that surround the galactic core like cosmic fingerprints. These shells are faint, sometimes barely a few percent brighter than the background sky, and yet they carry the unmistakable mark of an ancient celestial event, a galactic crime scene frozen in time. So what are shell galaxies really? And more importantly, what do they tell us about the nature of galaxies, gravity, and the dark interactions that mold the universe? The mystery of shell galaxies is not just in their structure, it's in their origin, their rarity, and the hidden stories they carry within their luminous folds. These shells, as it turns out, are relics of galactic cannibalism. Imagine a large elliptical galaxy pulling in a smaller, unsuspecting neighbor, a dwarf galaxy, perhaps, ripping it apart with tidal forces, consuming its stars and gas, and scattering its remains. As the smaller galaxy is torn apart, its stars don't just vanish. Instead, they move along orbital paths that eventually pile up at certain points, forming arcs, shells, like the way water might ripple outward when a rock is thrown into a still pond. Only here, the rock is a galaxy, and the ripples are composed of billions of stars. Most commonly, shell galaxies are thought to result from minor mergers, collisions between a large host galaxy and a much smaller one, usually a dwarf galaxy. As the smaller galaxy falls into the gravitational well of the larger one, its stars begin to orbit the center of the larger galaxy in elongated paths. Where these orbits slow down, at apocenters, the farthest points in their orbital journey, stars accumulate, creating the visible shells. Each shell marks a wave of stars that once belonged to the cannibalized galaxy. But the formation isn't as simple as a one-time event. Shells often appear in multiple concentric layers, and their spacing follows fascinating patterns that can reveal the timing and structure of the original merger. Some shell galaxies have as few as a couple of arcs. Others possess dozens. The spacing between the shells, the symmetry, and their orientation, all these features carry information about the mass of the galaxies involved, the angle of collision, and even the shape of the dark matter halo surrounding the system. One of the first and most iconic shell galaxies discovered was NGC 3923, located about 90 million light-years away in the constellation Hydra. Observed through powerful telescopes, it exhibits more than 20 concentric shells, an extraordinary number. The elegance of its structure stunned astronomers and hinted that these ghostly arcs might be more common than previously thought, provided we had sensitive enough instruments to detect them. Another extraordinary example is NGC 474, a peculiar-looking galaxy whose shell structures form swirling, asymmetrical loops, almost like petals of a cosmic flower. Observations from the Canada-France-Hawaii telescope brought NGC 474 into prominence, revealing a level of detail in its shell structure that had rarely been seen before. Some of its shells appear twisted, possibly due to multiple minor mergers or a collision with a galaxy on an oblique trajectory. These variations challenge astronomers to refine their simulations and test competing theories of galactic dynamics. Indeed, simulations have become one of the most vital tools in understanding shell formation. Cosmologists use supercomputers to simulate galaxy mergers, tracking the orbits of millions of individual stars. When they replicate the conditions of shell galaxies, they find that the resulting shells depend heavily on the type of orbit the smaller galaxy had, whether it was radial, plunging directly toward the host, or tangential, spiraling around it, and on how many times it circled before it was fully consumed. Each scenario produces different kinds of shells. Radial mergers result in more symmetric and concentric shells, while tangential interactions can create warped, overlapping structures. Shell galaxies do not merely present a visually stunning puzzle, they also serve as natural laboratories for understanding the invisible. Specifically, they provide an opportunity to probe dark matter. Since the shape, speed, and timing of shell formation is deeply affected by the gravity in and around the host galaxy, including the dark matter halo, researchers can use the shell structures to map the unseen. The symmetry of shells in some galaxies points to a spherical dark matter halo. Others, with offset or twisted shells, suggest more complex mass distributions, including triaxial dark matter shapes. This ability to test theories of dark matter distribution is vital. Most conventional methods of studying dark matter, like looking at galaxy rotation curves or gravitational lensing, focus on disk galaxies or clusters. Shell galaxies give astronomers a fresh angle, how gravity sculpts stellar remnants over time. By analyzing shell spacing and brightness, scientists can reverse engineer the shape of the gravitational potential, much like seismologists reconstruct Earth's interior from the paths of earthquake waves. Another curiosity about shell galaxies is their rarity, or at least, their apparent rarity. They are found primarily in elliptical or lenticular galaxies, especially those in isolated environments, where mergers can happen without being disrupted by nearby giants. But with better imaging technologies, such as those from the Hubble Space Telescope and increasingly powerful ground-based telescopes, we're beginning to find more shell galaxies than we once thought existed. Some may be hiding faint shells that only the deepest surveys can detect. As our view of the cosmos deepens, we may come to understand that many elliptical galaxies have ghostly pasts hidden beneath their smooth facades. Shell galaxies, in that sense, are not oddities, they're revealed histories. Every shell is a memory, a fossilized moment of violence, chaos, and rebirth. But the story doesn't end there. Some shell galaxies seem to defy current models. In a few cases, such as MCG 05-07-01, the shells are not simply luminous arcs in visible light. They are also detectable in X-ray emissions, hinting at complex interactions involving hot gas and possibly remnants of an active galactic nucleus. Others show multiple populations of stars within the shells, some much younger than expected, which raises new questions. Could shell galaxies be triggering star formation as gas from the disrupted galaxy compresses in arcs? Or are we looking at secondary accretions, with fresh galaxies falling into the system and contributing new layers of complexity? And then there's the philosophical allure of shell galaxies, the way they echo phenomena across scales. Their appearance is uncannily like the interference rings in fluid dynamics, or even the ripples left by supernova shockwaves. It begs a broader question about the patterns of the universe. Does the cosmos favor these ripple-like structures? Are shells a byproduct of universal laws of symmetry, or are they rare exceptions carved out by chaos? As technology advances, telescopes like the James Webb Space Telescope and future observatories like Louvre, Large UV Optical Infrared Surveyor, or the Nancy Grace Roman Space Telescope will give us deeper and clearer views of these faint structures. We may one day trace the complete life cycles of galaxies through the echoes of their shells, mapping the history of galactic interactions across cosmic time. In a way, to look at a shell galaxy is to glimpse into a mirror of the past, a fossil record of galactic violence, like bones beneath the dust of cosmic time. Yet even in their origins of destruction, shell galaxies offer something strangely poetic, a structure born from chaos, beauty from ruin, harmony from collision. In their faint arcs, they carry not just the remnants of what once was, but the promise of what still might be discovered. These faint arcs in the night sky, almost invisible to the naked eye, yet vivid in astronomical imaging, serve not only as snapshots of past mergers but as windows into the long-term evolution of galaxies. The more we study shell galaxies, the more we realize they are critical markers in a galaxy's journey from its formative years to its more passive, quiescent states. They are the scars left behind by growth, by assimilation, by the inevitable gravitational hunger that galaxies impose upon their smaller neighbors. Many of the galaxies we see today as peaceful ellipticals may not have always been so quiet. In fact, a majority of massive elliptical galaxies likely underwent several minor mergers throughout their histories. Shells, then, are not rare byproduct. They are essential evidence of a galaxy's cannibalistic diet. They are temporal footprints of cosmic events that occurred hundreds of millions, or even billions, of years ago. But because they fade with time, growing ever more diffuse and stretched, shell structures are ephemeral in astronomical terms. We may only be seeing a fleeting phase of these galaxies, a phase where memory still lingers in visible form. And therein lies another mystery. Why do some galaxies retain well-defined shells for so long, while others seem to erase these features rapidly? The answer likely lies in the combined influence of galactic dynamics, stellar velocities, and dark matter distribution. If the gravitational field is relatively smooth and symmetric, shells can remain coherent for longer. But if the field is disturbed by new mergers, tidal interactions, or internal asymmetries, the stellar arcs can quickly dissolve into the background, becoming indistinguishable from the host's halo. Yet there's more. Some shell galaxies display interleaved shell structures, meaning shells appear on alternating sides of the galaxy's center, like layered onion skins that have been sliced at an angle. These interleaved shells are thought to result from nearly radial orbits of the accreted stars. As the stars from the devoured galaxy oscillate through the host center, they reach turning points on opposite sides with each pass. The result is a kind of alternating pattern, a celestial rhythm that reveals the periodic motion of the disrupted stellar material. This naturally leads us to phase wrapping, a key concept in understanding shell formation. Phase wrapping occurs when a population of stars released from a single event, like a galaxy being torn apart, begins to oscillate through the galactic potential. Because stars at different radii orbit at different speeds, they start to stretch out over time. But at certain locations, apocenters, the stars slow down, bunch up, and form the visible shells. It's not that the stars are bound to the shell, rather, they are simply more densely distributed there. These are not permanent structures, but dynamic accumulations, gravity's traffic jams. Then there's space wrapping, another layer of complexity. This involves the spatial trajectory of the stars as they loop around the galactic core, not just in phase but in physical location. Combining both wrapping mechanisms can result in complex, nested structures that look remarkably like spiral shell patterns, or offset arcs depending on the original velocity dispersion of the infalling material. Some simulations even suggest that double mergers, where a galaxy consumes two satellites in rapid succession, can create overlapping shell systems with different orientations and depths. But what about shell galaxies in clusters or group environments? These settings are far more violent, with many galaxies gravitationally bound and interacting frequently. The high density of these environments often strips gas and disturbs tidal features, which makes shell formation harder and shell preservation even more unlikely. However, on rare occasions, shells do form even in these tumultuous regions, possibly aided by the gravitational focusing of encounters or mergers that occur on unusual, highly radial trajectories. When we do find a shell galaxy in a cluster, it becomes an especially important case study, providing insights into how these structures can survive despite environmental hostility. The study of shell galaxies also intersects with another cosmic puzzle, galactic halos and their shape. If the dark matter halo of a galaxy is spherical, shells tend to appear more concentric and evenly spaced. But if the halo is triaxial, more football-shaped or cigar-shaped, the shells become warped, twisted, or even duplicated. This means shell galaxies can be used as cosmic gravitational probes, indirect tools for mapping the otherwise invisible scaffolding that holds galaxies together. This technique, using visible matter to infer the behavior of dark matter, is not new, but shells offer a more geometrically elegant probe than the usual techniques like rotation curves or lensing distortions. The spacing of shells, when measured carefully, allows astrophysicists to reconstruct the gravitational potential, much like a sonar system maps the ocean floor using echoes. In that sense, every shell in a galaxy is an echo of the merger, yes, but also an echo of the underlying gravity itself. But beyond mechanics and structure lies the larger, more poetic vision of shell galaxies. They embody the paradox of cosmic evolution. Their arcs are remnants of destruction, yet they form patterns of serene symmetry. They are born from chaos, but they whisper order. They are scars, and yet they are beautiful. One cannot help but be struck by the visual similarity between shell galaxies and certain terrestrial phenomena. Think of the ripple marks left by a tide withdrawing from the shore, or the concentric rings formed when a raindrop falls into still water. These echoes of impact across vastly different scales speak to something fundamental about the universe. That pattern often emerges from turbulence, and that even violence leaves behind a kind of quiet legacy. From an observational perspective, detecting shell galaxies remains one of the more challenging tasks in extragalactic astronomy. Their faintness requires long exposures and deep imaging. Many shell features are only visible under specific lighting conditions, often in the outermost regions of galaxies where light levels are extremely low. Some of the most successful surveys, like the MATLAS, Mass Assembly of Early Type Galaxies with their Fine Structures survey, have focused on uncovering such low surface brightness structures. These projects have dramatically expanded our knowledge, revealing that shell galaxies are likely far more common than previously assumed, just more subtle. The real revolution may come from next-generation observatories and AI-enhanced image processing. Machine learning algorithms are already being trained to sift through vast astronomical archives to identify faint shell structures that human eyes might miss. These tools not only boost discovery rates but can also help classify shells by type, age, symmetry, and potential origin. With enough data, we may even begin to piece together a taxonomy of shell features, allowing us to read a galaxy's history like a biography etched in starlight. More exotic theories have also emerged around shell galaxies. Some researchers have speculated about shell formation driven by alternative gravity models, such as modified Newtonian dynamics, (MOD). These ideas are controversial but valuable, as they force astrophysicists to test whether dark matter is truly the best explanation for shell behavior, or if other forces might be at play. Similarly, studies of shell galaxies in simulated universes, where different rules of physics can be applied, allows scientists to explore what-if scenarios and test how sensitive shell formation is to changes in gravitational laws. Even more speculative are theories tying shell structures to early universe conditions. Could some shells be remnants not of modern mergers but of ancient interactions from the cosmic dark ages? Could primordial dwarf galaxies have seeded these structures long before the current era of star formation? These remain open questions, but they highlight how shell galaxies can become tools not just of astrophysics, but of cosmic archaeology, tracing the large-scale narrative of the universe's own developmental history. In some rare and bizarre instances, astronomers have identified galaxies that display both shell features and signs of active galactic nuclei (AGN). This creates an interesting intersection between large-scale stellar dynamics and supermassive black hole activity. If AGNs are triggered by mergers, through the infall of cold gas feeding the central black hole, then shell galaxies could represent a post-merger phase where the AGN has either recently ignited or is in the process of shutting down. Observing these galaxies could provide valuable insights into how the feeding cycles of black holes relate to galactic structural changes. Then, there's the existential allure of shell galaxies. Unlike spiral arms, which constantly regenerate, or starbursts, which come in cycles, shells are often one-time events. Their presence is a eulogy for a lost companion, a moment of history frozen in celestial geometry. When we observe a shell galaxy, we're not just looking at a structure, we're witnessing a ghost. The stars in those arcs belong to another galaxy, one that no longer exists. Its identity is gone, its shape destroyed, its core likely dissolved. And yet, through gravity, through orbital mechanics, through the elegant laws of motion, its memory persists. To stare into a shell galaxy is to stare into the past, and not just any past, but a past written in blood and beauty, in gravitational violence and stellar grace. In a universe that is constantly changing, constantly evolving, shell galaxies remind us that some stories, though quiet and delicate, never completely fade. And in that persistence, those faint, glimmering arcs against the blackness of the cosmos, we find not only a chronicle of galactic assimilation, but a metaphor for memory itself. Shell galaxies are the sky's version of faded fingerprints, a map of old entanglements whose consequences ripple across billions of years. They are composed of stars, yes, but also of evidence, testimonies to long-lost galaxies whose final fate is to become decoration, ornaments around the body of their devourer. This idea, that galaxies remember, gives shell galaxies a special place in modern astrophysics. Just as tree rings tell the story of climate changes or tectonic plates remember earthquakes, these stellar arcs preserve records of timing, motion, energy, and violence in a frozen form. Every arc has a time signature. Every curvature and thickness encodes the dynamical evolution of a system no longer whole. When astrophysicists simulate these mergers using particle dynamics and gravitational equations, they can reproduce such arcs almost precisely. This ability to recreate the shells in computer models validates the theories about their origins and provides confidence in the physical laws shaping our universe. But even the best simulations cannot fully capture the chaotic beauty of reality. Nature always adds its own noise, its own asymmetries, its own surprising irregularities. Some shell galaxies defy expectations entirely, displaying misaligned or incomplete arcs, or asymmetric patterns that seem to twist or curve unnaturally. These features may point to more complex histories. Perhaps the merger involved not one but multiple galaxies in a cluster environment, or perhaps the shells are being warped by an unseen mass, like an invisible satellite galaxy or a dark matter clump nearby. In recent years, astronomers have even begun to explore the possibility of dark shells, structures similar to luminous shells but composed primarily of dark matter or extremely faint stars. These would be invisible to standard telescopes but might betray their presence through gravitational effects, like weak lensing or subtle distortions in the orbits of visible stars. Though purely theoretical at present, the notion of dark shells is fascinating. If confirmed, they could open an entirely new chapter in the study of galactic archaeology, one where we reconstruct not just the luminous past of galaxies, but their invisible history as well. Furthermore, there's increasing evidence that shell galaxies may influence their surroundings in more profound ways than we imagined. The gravitational reach of their shell structures could potentially perturb smaller satellite galaxies, redirect gas flows, or even trigger secondary star formation events in surrounding space. This connects shell galaxies not only to the past but to the future evolution of their environment, making them dynamic agents in the cosmic web. Their uniqueness has also made shell galaxies subjects of aesthetic admiration. Some of the most compelling astronomical images feature galaxies like NGC 7600, with its delicate, ripple-like arcs against a smooth elliptical background. The artistry of these structures has drawn the attention of science communicators, artists, and even filmmakers, as symbols of ancient memory or cosmic conflict. They look sculpted, arranged, as if the universe had an artistic side, using gravity as a chisel and stars as its medium. Looking into the sky and seeing such an image evokes a sense of timelessness. We're not just observers. We become readers of the universe's diary, deciphering entries written in luminous code. And each shell galaxy is a new page, telling a different story, one of a collision, a loss, and a transformation. It forces us to consider how violent the universe truly is, yet how out of that violence can emerge something so quietly profound. This duality, violence and beauty, chaos and structure, is one of the defining features of shell galaxies. They exist in that narrow space where science becomes poetry, where mathematics describes art. When astronomers measure the curvature of a shell, or the radial velocity of the stars within it, they are engaging in a kind of forensic science. They are reverse engineering an ancient event, decoding the fingerprints left by the past. In doing so, they affirm that the universe is not just expanding, it is remembering. Consider the timescales involved. A typical shell galaxy might have formed its shells several hundred million years ago, perhaps more. And yet those shells remain, slowly fading, shifting, stretching as the stars move along their orbits. Each shell is effectively a phase space caustic, a place where the orbits of many stars align in both space and time. These are moments of maximum density in otherwise sparse fields of motion. It's like all the stars happen to pause and sync, just for a moment, creating a ripple of brightness in an otherwise dark halo. Over time, these shells spread, dissipate, and eventually vanish into the galaxy's general field of stars. But for a while, they persist, bold, elegant signatures of something no longer there. Even more incredible is the possibility that our own Milky Way may have once had or may still have shell-like features hidden deep within its halo. Some streams and overdensities detected by deep sky surveys like Gaia hint at past mergers and accretion events that could, in time, produce shell structures. If we could map the outer halo of the Milky Way in sufficient detail, tracing the orbits of old stars, we might find evidence that we too are the product of galactic consumption, that our own cosmic history is just as layered and haunted as that of NGC 3923 or NGC 474. In this context, shell galaxies become more than objects of study, they become mirrors. They reflect not only the mechanics of galactic interaction, but the fate of all galaxies, including our own. The universe is a place of constant assembly, where structures are built from collisions and expanded through assimilation. Nothing is static. Every large galaxy is a survivor, a composite, a relic of past unions and silent devourings. This understanding reframes our place in the cosmos. We tend to think of the stars as eternal, galaxies as permanent. But shell galaxies remind us that permanence is an illusion. What seems serene and unchanging is often the result of immense transformation. The galaxy we see today may be the graveyard of others. And just as surely, it will become part of something larger in the future. Technologically, our ability to observe shell galaxies is poised to explode. Telescopes like the Vera C. Rubin Observatory will soon scan the entire southern sky with unprecedented sensitivity. Its 10-year legacy survey of space and time, LSST, is expected to find thousands of previously hidden shell galaxies. These will span a vast range of environments, redshifts, and morphologies. Combined with the deep infrared imaging of the James Webb Space Telescope, this will allow scientists to trace the evolution of shell galaxies across cosmic time, from the relatively nearby universe all the way back to its early epochs. Imagine mapping shells at redshift 1 or higher, shells from a time when the universe was just a few billion years old. That would push the frontier of shell studies into the epoch of major galaxy formation, giving us a glimpse into the early mechanics of cosmic growth. By comparing young shell galaxies to ancient ones, we might identify trends in how galaxies grow, evolve, and interact across time. These comparisons could even reveal how the nature of dark matter or the laws of gravity themselves may have shifted or expressed differently in the distant past. The next decades will be a golden age for shell galaxy science, not just in terms of quantity, but quality. With 3D mapping of stellar velocities, machine learning-assisted structure identification, and high-resolution modeling of mergers, we will reach a level of detail that allows us to not just observe shell galaxies, but to fully reconstruct their formation histories. It may even become possible to identify individual stars that were once part of a disrupted satellite galaxy, stars that now trace the arcs of a shell, each one a wandering remnant of a civilization-sized structure, now dissolved. One can imagine an astronomical future where we catalog these stars like historians catalog ancient ruins, marking their origins, tracking their paths, and weaving them into the larger story of the cosmos. Shell galaxies thus represent one of the most elegant intersections of physics, history, and beauty in the known universe. They are archives. They are sculptures. They are echoes. And as we continue to observe them, through new instruments, new simulations, and new eyes, we inch closer to a complete understanding of how galaxies grow, how they interact, and how they remember. The next time you look up into the sky, know this: somewhere out there, a ghost of a galaxy is still glowing faintly in the night, caught in the graceful arms of the one that devoured it. And as these celestial ghosts drift through the galactic halo, they do not simply fade quietly into oblivion. Their continued presence in the form of shells ensures that the memory of their existence lingers, not just in the stars they left behind, but in the gravitational ballet those stars continue to perform. Long after their cores have been absorbed and their original structure erased, these galaxies live on, etched into the fabric of their host's outskirts like fossilized waves in cosmic sand. It's almost haunting to think that the universe itself carries memory not in writing, not in sound, but in structure. The cosmos remembers through motion, through resonance, through layers of disruption that settle into harmony. Each shell is a sentence in the universe's autobiography, one not written in ink, but in orbits. And because of this, the more shells we observe, the more fluent we become in this silent language of the stars. Astrophysicists have begun to explore how shell kinematics, the specific motion of stars within these arcs, can be used to date the merger event that caused them. By measuring how quickly stars are moving within the shell, and understanding the gravitational potential they move through, researchers can backtrack the timeline to estimate when the collision occurred. This has revealed something unexpected. Some shell galaxies are much younger than we previously believed. Others are ancient, still bearing marks from mergers that happened before complex life evolved on Earth. There is something deeply humbling in this realization, that long before our solar system formed, two galaxies may have collided in deep space, and the fading memory of that event is only now being observed, deciphered, and understood. It places our existence, our technology, and our civilization into cosmic perspective. We are latecomers reading the end of a chapter written eons ago. These revelations also complicate our understanding of galactic morphology. Traditionally, galaxies were classified into ellipticals, spirals, and irregulars, a kind of cosmic zoo with seemingly clear boundaries. But shell galaxies blur those boundaries. Many of them appear elliptical at first glance, yet their shell structures hint at complex, dynamic pasts involving spiral progenitors or irregular mergers. This has led some researchers to propose that the Hubble tuning fork model of classification is overly simplistic, especially when we consider how many galaxies carry hidden scars beneath their luminous facades. Shell galaxies, in this light, become the missing link between past galactic forms and present ones. They suggest that every galaxy is a process, not a product. That what we see today is merely a snapshot in an unending transformation. Their very existence demands that we study galaxies not just in space, but across time. Moreover, shell structures are not just limited to massive elliptical galaxies. Observations have found shell-like features even in dwarf galaxies, though far fainter and more subtle. These shells, more vulnerable to disruption, suggest that minor mergers between even smaller systems might produce similar echoes on a diminutive scale. This raises the possibility that shell formation is a universal outcome of gravitational merging, regardless of scale, a phenomenon as prevalent in dwarf groups as in giant galactic clusters. Interestingly, the smallest shell systems observed are so faint and ephemeral that they barely register in optical images. It's only through image stacking, ultra-deep surveys, and advanced processing techniques that we're able to pull them from the noise. These techniques act as time machines, revealing structural fossils buried beneath the surface brightness limits of most telescopes. Each new detection deepens our understanding of how common these features might be, and how much of galactic history remains hidden in plain sight. There's also an increasingly important role for citizen science in this endeavor. Projects like Galaxy Zoo have enlisted thousands of volunteers to identify unusual galaxy features, including shells, ripples, and streams. These efforts have uncovered shell galaxies previously overlooked by automated systems, proving that human pattern recognition still plays a vital role in the frontier of space exploration. Combined with machine learning and deep learning classification, citizen observations are helping to create massive datasets that can be used to probe statistical trends in shell formation across different environments. As we gather more of these shells into our catalog, patterns begin to emerge. Shells tend to occur more frequently in low-density environments, where galaxies are more isolated and can interact without being stripped or violently perturbed by nearby giants. In contrast, denser clusters often erase shell features quickly due to tidal forces and rapid encounters. This makes shell galaxies valuable probes of galactic solitude, telling us where galaxies had the space and time to engage in quiet mergers rather than violent collisions. Even more curious is the discovery that some galaxies exhibit shells without any nearby companions, past or present. These orphan shell galaxies puzzle astronomers. Were their companions so thoroughly destroyed that no trace remains? Or were they formed by an entirely different mechanism? One theory is that such galaxies experienced cold accretion flows, rivers of primordial gas that fed the galaxy from intergalactic space. If stars formed along these filaments, their motion could mimic shell-like patterns under the right conditions. If true, it would suggest that not all shells are created from mergers. Some might be born from the geometry of cosmic gas inflows. Another theory posits that resonant interactions with dark subhalos, lumps of dark matter too small to host their own stars, could stir a galaxy's outer halo in ways that resemble shell formation. Though speculative, this idea opens a tantalizing possibility that we might one day detect dark satellites not by their gravity alone, but by the ripples they leave in stellar structures. In this way, shell galaxies could serve as detectors of dark matter behavior, providing indirect but persuasive evidence of the invisible scaffolding of the cosmos. And then there's the emotional and philosophical resonance of shell galaxies. For many, these structures inspire more than scientific curiosity. They awaken a sense of cosmic nostalgia. In the spiraling arcs and fading light of these shells, we glimpse the passage of time on a scale that dwarfs our own. These galaxies are tombstones and testaments, both tragic and beautiful. They are what remains when the fire of a galactic collision burns out and leaves behind only geometry and starlight. Astronomy has always been a search not only for knowledge, but for meaning. In shell galaxies, we find a convergence of the two. They are deeply physical, obeying the strictest laws of dynamics, conservation, and energy exchange. But they are also symbolic, standing as evidence that the universe keeps its history close, that every act of creation comes with a trail of echoes. Shell galaxies are, quite literally, the outlines of absence. The arcs we observe are composed of stars that no longer orbit a common center but now follow new trajectories in a foreign gravitational field. Their shared origin is gone, yet their shared path remains. This is the paradox of shells. Their source no longer exists, and yet they are inseparable from it. And that paradox is perhaps the greatest mystery of all. In a universe governed by entropy, where all things tend toward disorder, the shell galaxy is a testament to fleeting symmetry, a temporary reversal of chaos into coherence. It is a momentary hush in the cosmic storm, a ripple of remembrance. As our instruments sharpen, as our models grow more sophisticated, and as our understanding deepens, we will continue to peel back the layers of these galaxies, arc by arc, shell by shell. We will trace each curve, each ripple, each faint whisper of light until we have heard the full story of the galaxy that once was. And perhaps, in doing so, we will come to understand not just how galaxies die or transform, but how the universe, in its silence, refuses to forget. Shell galaxies are more than just evidence of galactic mergers. They are time capsules, each arc a preserved artifact from an ancient cosmic drama. And yet, even as we try to piece together these narratives with our current instruments, the future holds potential for revelations that may completely reframe how we see them. The data we collect from new generations of space telescopes will allow us to observe shells with far greater sensitivity, resolution, and reach, pushing the frontiers of our understanding into even more remote and enigmatic corners of the universe. In particular, the Nancy Grace Roman Space Telescope, expected to launch in the coming years, will revolutionize our view of low-surface brightness phenomena like shells. Its wide-field infrared vision will let us probe deeper into the halos of galaxies than ever before. What was once hidden noise will become structure. What was once invisible will become identifiable. Roman's ability to capture large areas of sky at once, while preserving exquisite detail, will likely uncover tens of thousands of new shell systems. We may finally begin to answer the question, how common are shell galaxies, really? Are they rare exceptions, or are we simply not seeing the majority of them due to our observational limitations? But it's not just about seeing more shells, it's about understanding their fine structure. Future observations will help us distinguish between different kinds of shells, those that are sharp and thin, indicating a relatively recent, high-energy merger, and those that are broad and diffuse, perhaps remnants of much older or multiple interactions. These distinctions will allow astrophysicists to reconstruct precise timelines, piecing together the dynamic biography of each galaxy with forensic clarity. What's especially fascinating is the emerging idea that shells could act as tracers of exotic phenomena, such as the behavior of modified gravity or alternative dark matter models. For instance, in modified Newtonian dynamics, MOND, or self-interacting dark matter scenarios, the evolution of shell structures could differ subtly from predictions made under classical Newtonian gravity and cold dark matter. By studying shell systems with extreme detail, astronomers hope to detect tiny deviations that could validate or falsify entire cosmological theories. Moreover, there's a growing curiosity in whether supermassive black holes at the centers of galaxies can influence shell formation. While central black holes are mostly thought to impact core regions, their gravitational influence might subtly alter the distribution of stars in the outskirts, especially during or after a merger. Could some shell features be warped by the presence of a rapidly spinning black hole? Could shells be disrupted, enhanced, or even shaped into unusual geometries depending on black hole mass or motion? These are questions that remain on the edge of theoretical exploration. In the most imaginative corners of astrophysics, researchers have even asked, could shell structures host habitable systems? It's a speculative question, but one that touches on the deep intersection between structure and life. While shell regions tend to be sparse and dynamically unstable over long timescales, it's not entirely impossible that some of the stars within these shells host planetary systems. These planets would reside in a strange environment, either within the dense core of a galaxy nor entirely outside it, but drifting across a stellar echo. If life exists there, it would see the host galaxy rise in the sky as a luminous orb surrounded by curling streams of ancient stars, a breathtaking panorama of a galactic monument to destruction. Such musings add a human dimension to the study of shell galaxies. They invite us not only to observe, but to imagine. What would it be like to witness the unfolding of a shell system from within? What would time feel like if marked not by seasons, but by the drifting of arcs and streams of stars across the night sky? Indeed, many science fiction writers and visual artists have drawn inspiration from these majestic systems. The concept of galactic ghosts, of civilization swallowed in interstellar collisions, of memory etched in light, has found its way into stories, films, and paintings. Shell galaxies offer not just a canvas for science, but for creativity, an invitation to explore the intersection of physics and philosophy. And philosophically, few structures in the universe confront us with the idea of impermanence so vividly. Galaxies, which we often imagine as immutable, colossal, eternal, are in fact vulnerable, capable of being unraveled and reshaped by the gravity of others. Shell galaxies remind us that even the grandest systems are not spared change. They are not fortresses, but vessels, open to the currents of the cosmic sea. This, in turn, evokes one of the most powerful themes in astronomy: the unity of destruction and creation. The merger that forms a shell galaxy is an act of erasure, but also one of renewal. The stars of the consumed galaxy are not destroyed, they are redistributed. Their orbits find new harmony in the gravitational landscape of their captor. The arcs they form are not scars, they are rebirths. The same force that tears galaxies apart gives rise to beauty that endures across billions of years. In a sense, shell galaxies become cosmological cathedrals, built not by design, but by the laws of gravity and motion. Their arcs are windows into ancient events. Their silence speaks of grandeur and loss. They remind us that time in the universe does not erase, it rearranges. And perhaps this is the most important lesson shell galaxies offer us. In our own lives, we tend to think of loss as disappearance. But the cosmos tells a different story. It tells us that everything that was still is, in some form. That the stars which once belonged to a vanished galaxy still shine, still orbit, still move in silent unity. That from the chaos of collision comes order, and from the fragments of destruction comes structure. As we stand on the precipice of new discoveries, shell galaxies will continue to be one of the most evocative windows into the soul of the universe. They speak of memory without mind, of history without witness, of motion without meaning, until we, the observers, arrive to assign it. We read their arcs like glyphs on ancient walls. We translate their orbits into timelines. We turn their silence into story. And in that story, we find ourselves. For we, too, are made of remnants. Of stardust from dead stars. Of atoms forged in supernovae. Of molecules shaped by chaos and order alike. The universe remembers, and so do we. Shell galaxies are its way of saying, nothing truly disappears. Everything leaves a trail. We just have to learn how to see it. As we refine our ability to detect and interpret shell galaxies, we begin to realize that these structures are not rare cosmic flukes. They may be far more ubiquitous than previously imagined. But their faint nature makes them easy to overlook. Most telescopic surveys are designed to catalog bright galaxies and sharp features, often neglecting the diffuse, ghostly remnants that lurk on the fringes. This is especially true in older astronomical datasets where short exposure times and limited dynamic range mask the true extent of galactic halos. Now, with modern image processing and ultra-deep surveys, what was once invisible is steadily coming into view. One of the most significant advancements in this field has been the application of low-surface brightness imaging techniques. Instruments like the Dragonfly telephoto array, a telescope designed specifically to image ultra-faint structures around galaxies, are revealing the rich complexity of galactic halos. With its innovative lens design and superior ability to reduce internal scattered light, Dragonfly has been instrumental in spotting shell-like structures in galaxies that were previously considered featureless. These observations are not just academic. They point to a deeper truth, that most galaxies carry scars from past interactions, and that the elegant smoothness we often associate with elliptical or lenticular galaxies may be deceptive. Beneath the light we can see lies a deeper narrative, painted in arcs and curves and asymmetries. Shells, in this view, become not exceptions but evidence of a universal process, hierarchical assembly. According to the lambda cold dark matter model, large structures in the universe form through a continual series of mergers. Small galaxies merge to form larger ones, and so on, building complexity over billions of years. Shell galaxies serve as the visible bookmarks of this process. They confirm that the growth of galaxies is not smooth and steady but violent and episodic, driven by collision and consumption. But here's where the mystery deepens. Not all galaxies exhibit visible shell structures, even if they've likely undergone similar merger histories. Why is that? Could it be that some galaxies are better at hiding their past? Or that certain types of mergers leave no detectable shells? This introduces an element of forensic astronomy, analyzing what is not seen to infer what must have happened. Simulations offer one possible explanation. Models show that the visibility of shells depends on viewing angle, time since merger, orbital geometry, and the contrast between the merging galaxies' mass and stellar populations. If the merger was too ancient, the shells may have dispersed. If the orbital parameters were unusual, the resulting structures may not resemble the classic interleaved arcs we associate with shell systems. Even the composition of the stars, whether they are metal-rich or metal-poor, can influence how visible they are at various wavelengths. This means we're looking at a layered phenomenon, shaped by both physical dynamics and observational limitations. Some galaxies may have hosted shell structures long ago, only to see them dissolve into the stellar halo with time. Others may possess shells so faint, or so skewed in perspective that they escape our detection entirely. Understanding these variables is key to building a more complete census of galactic histories. Meanwhile, at the theoretical edge of the field, researchers have begun exploring whether shell galaxies might encode information about dark energy, the mysterious force driving the accelerated expansion of the universe. It's an ambitious idea, but the logic is compelling. If shell galaxies can act as cosmic clocks, marking time since merger, and if their distribution can be mapped across vast distances, they might serve as indirect tracers of cosmic expansion. A shell galaxy observed at great distance is not just an isolated object, it is a snapshot in time. If we can measure the properties of its shells accurately enough, we might use them to constrain the timeline of cosmic growth and, by extension, refine our models of dark energy. This turns the humble shell galaxy into a kind of cosmic chronometer, quietly recording epochs of interaction and change. It's an extraordinary thought, that long after two galaxies collided, long after their shapes were warped and fused, the faint ripple of that event continues to echo across space, telling us not just what happened, but when. These echoes may also carry gravitational signatures detectable through stellar velocity dispersion studies. Shell structures tend to form in specific kinematic environments. Stars in each shell orbit with a certain characteristic speed and energy. By measuring these velocities across shells, scientists can reconstruct the gravitational potential of the host galaxy, even at large radii where dark matter dominates. In effect, shells offer a natural laboratory for studying galactic dark matter halos, how massive they are, how far they extend, and how they influence stellar dynamics. This opens up a new avenue for dark matter research. While gravitational lensing remains the gold standard for mapping dark matter distributions, it often requires rare alignments and massive foreground objects. Shell galaxies, on the other hand, are self-contained systems whose internal dynamics can yield direct insights into the invisible mass that envelopes them. Yet even as we learn more, some shell galaxies continue to defy explanation. There are those with asymmetrical shells, mismatched arcs, or discontinuous layers. Some systems have inner shells that rotate in a different direction than outer ones. Others exhibit polar shells, oriented perpendicularly to the main disk of the galaxy. These anomalies hint at even more complex merger scenarios, possibly involving multiple galaxies, or interactions between a galaxy and a dense globular cluster system. Each of these outliers forces theorists to revise assumptions, test new models, and confront the limits of current understanding. In some cases, the only way to explain the observed shell configuration is to posit multiple merger events, a kind of cosmic pinball where a galaxy has absorbed more than one companion over time, each leaving behind its own pattern of ripples. These complex shell systems may represent galaxies that have grown through serial accretion, building mass layer by layer in a process that spans billions of years. As these scenarios are modeled and refined, they contribute to a galactic genealogy, a kind of stellar ancestry tracing back through time. Shells are no longer just pretty features. They are evidence chains, linking present structures to past events. They tell us not only that galaxies evolve, but how, when, and under what conditions. Perhaps the greatest mystery shell galaxies pose is this: what do they imply about our own galaxy's past? The Milky Way, like all large galaxies, must have undergone mergers. Indeed, its halo contains streams of stars, like the Sagittarius stream, that are believed to be remnants of past interactions. But does our galaxy also harbor shell structures? Some simulations suggest that shells could exist in the Milky Way's outermost regions, far beyond the visibility of most sky surveys. These structures would be incredibly faint, overlapping with the diffuse halo and intermingling with countless stellar streams. Detecting them would require new techniques, perhaps instruments orbiting beyond Earth, capable of imaging faint light from the galactic periphery without interference from local stars and dust. If shells do exist around the Milky Way, they might offer insights into the timing and nature of its past mergers, possibly revealing events not yet documented. And if they don't, if we find that our galaxy lacks visible shells, then that, too, would raise questions. Was our merger history different? Were the interactions more ancient? Or has the Milky Way simply had enough time to erase the evidence? Each possibility carries profound implications, not just for galactic science, but for our place within the cosmos. If the Milky Way's outer reaches harbor shell-like structures, their detection would mark a turning point in galactic archaeology. It would mean that the fossil record of our own galaxy is not buried in some ancient alien world or distant deep space system. It's right here, in the sky above us, spread thin across the galactic halo like a cosmic fingerprint. To find such shells, astronomers would need to examine vast regions of sky with extreme sensitivity. Future surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSSD, are expected to produce an unprecedented trove of ultra-deep, wide-field imagery. Over its 10-year mission, LSSD will repeatedly scan the sky, enabling astronomers to stack thousands of images for each region, pushing the limits of detection for faint features. If shells exist around the Milky Way, or in the outskirts of nearby galaxies, they may finally reveal themselves in this new observational epoch. But beyond mere detection lies the challenge of interpretation. Even if shells are found, their origins must be reconstructed with painstaking analysis. That means tracing the stellar populations within each shell, analyzing their ages, metallicities, and velocities. Are they mostly old, red stars, or do they include younger blue ones? Are their orbits consistent with a single past merger, or are they a composite of multiple infall events? It's here that galactic forensics transforms into something almost poetic, a science of memory, using light and motion to rebuild a story long vanished. And yet there's something almost melancholic about shell galaxies. They are monuments to destruction, yes, but not chaos. They are ruins that took form through order. The stars within them are not wreckage. They are liberated, unchained from their original orbits, now bound in sweeping arcs across their new host galaxy. Each shell is a wave of stellar migrants, echoing outward like the final notes of a symphony long since ended. What survives is not the original galaxy, but its legacy, reinterpreted, rearranged, and reframed by time. There's a certain quiet violence in this process. In the realm of human affairs, the destruction of one civilization by another is fraught with tragedy. But in space, such events are inevitable. Gravity makes no moral judgments. It does not ask permission. It simply draws the weak toward the strong, reshaping structure through motion, turning disorder into form. Shell galaxies are not warnings, they are records. And we are just beginning to learn how to read them. The aesthetic beauty of shell galaxies cannot be overstated. Some are nearly perfect, their arcs arranged like petals around a cosmic flower. Others are lopsided and fractured, suggesting more chaotic mergers or turbulent intergalactic environments. In either case, the result is stunning, structures of light that defy everyday geometry, spiraling and rippling in ways that seem more like abstract art than physics. Their elegance is deceptive, though. Beneath their curves lie violent gravitational dynamics, collisions that flung billions of stars across hundreds of thousands of light years. And those stars, silent and ancient, continue their paths unbothered, unaware of the cosmic story we project onto them. In fact, some researchers believe that we may not yet have a full theoretical framework for how shells evolve over long timescales. Many models predict that the arcs should eventually blur into the general stellar halo, becoming indistinguishable over billions of years. But the persistence of shells in some systems suggests otherwise. Why do some galaxies preserve their shell patterns for so long, while others do not? Are we missing some stabilizing mechanism, perhaps related to dark matter or to specific orbital alignments, that allows shells to endure? This opens the door to next-generation simulations, leveraging advances in computational astrophysics and AI-based modeling. With enough resolution and physical fidelity, we may one day simulate the full life cycle of a shell galaxy from first contact through full merger and long-term relaxation. Such simulations could reveal previously hidden phases of shell evolution, perhaps even transient stages where new shells emerge from secondary interactions or core oscillations. Indeed, recent models suggest that in some cases, shell structures can regenerate. As the core of the galaxy oscillates post-merger, essentially sloshing under the residual gravitational momentum, it can create secondary waves of stars, forming new shells in different orientations. This challenges the idea that shells are purely a byproduct of the initial collision. Instead, they may be part of a longer, more dynamic equilibrium process, where the galaxy settles into its new configuration gradually, through multiple pulses of stellar redistribution. This concept of galactic sloshing leading to shell regeneration brings shell galaxies closer to phenomena like ring galaxies or tidal tails, where the gravitational rebound following an impact generates concentric or spiral structures. It highlights the complexity of gravitational interactions and the way in which even post-merger galaxies can remain energetically alive, vibrating with the residual memory of their past. In this light, shell galaxies begin to resemble not just aftermaths, but living systems, changing, adapting, and expressing the invisible rhythms of gravity in visible form. They're not just galactic fossils, they're ongoing processes, unfolding slowly across cosmic time. And this leads us to an even deeper mystery. What role do shell galaxies play in cosmic structure formation at large scales? If shell-forming mergers are common, and if these events significantly alter the mass distribution within galaxies, then shell galaxies may influence the growth of galaxy clusters, filament formation, and even the large-scale gravitational lensing effects that we use to map the universe. Could it be that shell structures introduce subtle biases into our mass models of the cosmos? Could they be influencing the statistical properties of galaxies in ways we haven't accounted for? As we build more detailed galaxy surveys and try to map dark matter on intergalactic scales, these questions become increasingly relevant. On the observational side, the next few decades promise breakthroughs that could completely transform this field. Projects like the Square Kilometre Array, SK, will allow astronomers to map neutral hydrogen gas in and around galaxies with unmatched sensitivity. While shells are primarily stellar structures, they may be accompanied by faint gas features, remnants of the original interstellar medium of the disrupted galaxy. Detecting such gas would add a new dimension to our understanding of shell formation, helping to constrain gas dynamics during mergers and revealing how star formation is influenced by these interactions. At the same time, the James Webb Space Telescope, JWST, though focused on deep space and early galaxies, could serendipitously detect shells in high-redshift galaxies, providing a glimpse into whether this phenomenon existed in the young universe. If so, it would suggest that shell galaxies are not merely a byproduct of the relatively quiet, modern universe, but a fundamental component of galactic evolution even in its earliest chapters. These new tools will extend our reach in space and time, allowing us to see not only more shells, but older and younger shells, building a kind of time-lapse of galactic interaction across the entire history of the cosmos. In this journey of discovery, shell galaxies remind us that the universe is not static. It is a constant negotiation between creation and collapse, between structure and entropy, between the invisible hand of gravity and the radiant aftermath it leaves behind. As our instruments sharpen and our reach deepens, we must begin to rethink not just what shell galaxies are, but why they matter. They are no longer merely curiosities on the periphery of galactic morphology. They are evidence of the cosmic narrative, etched into the structure of galaxies like scars across ancient ruins. And what's most compelling about them is their universality. The conditions that produce shell galaxies are not rare. Mergers, gravitational cannibalism, and tidal interactions are central to the way the universe evolves. Shell galaxies are, in effect, the cosmic norm temporarily laid bare in a uniquely elegant way. Yet they also speak to something more philosophical, the beauty of aftermath. In our human view, collision and destruction often connote tragedy. But in the language of the cosmos, these terms lose their sting. A galactic collision isn't the end of a galaxy's story, it's the beginning of a new one. Shell galaxies embody this transition. They are neither the original form nor the final structure, but the transitory whisper of change made visible. That whisper is not always soft, however. Some shell galaxies exhibit shells that are so dynamically active and dense that they can trigger secondary star formation. These are particularly intriguing because shells are usually composed of older, redder stars, the ancient remains of a cannibalized dwarf galaxy. But in some systems, the compression of interstellar material along the arcs causes new stars to ignite. This leads to blue-tinged shells, younger and hotter, sparking like fireflies in a storm. These rare cases suggest that shell galaxies may not only be records of the past, but incubators for the future, nurseries of stellar rebirth rising from the ashes of cosmic collision. In this way, they link past and future through a present shaped by structure and resonance. Then there are the multi-shell galaxies, such as NGC 3923, which boasts over 20 discernible shell structures, more than almost any other known galaxy. This elliptical galaxy has become a kind of Rosetta Stone for shell dynamics. The precision and number of its arcs have made it a testbed for gravitational modeling, and for probing the dark matter profile of elliptical systems. Strangely, The shells of NGC 3923 show a level of spacing regularity that exceeds what simulations predicted. This has led to debates. Are we missing a key physical mechanism? Are the shells stabilized by some unseen configuration of dark matter? Or was the merger scenario itself unusually symmetric? Some researchers have gone further, suggesting that anomalies in shell spacing could hint at modified theories of gravity, such as MOND, modified Newtonian dynamics. While controversial and largely unsupported in broader astrophysics, these ideas reveal just how sensitive shell structures are to gravitational environments. If anything can act as a natural probe of gravity on galactic scales, it is a shell system, where stars are thrown into extreme orbits and settle into delicate patterns that reveal the nature of the force holding them. This is especially significant in dark matter-dominated regimes, where the luminous components of a galaxy provide only a fraction of the total mass. In these zones, shell dynamics offer a unique way to test whether our models of gravity, Newtonian, relativistic, or otherwise, still hold true. Are the shells obeying the rules of classical mechanics, or are they subtly diverging in ways that betray the influence of dark energy or some deeper gravitational symmetry? In the pursuit of answers, researchers are now turning to machine learning algorithms trained on simulated shell galaxies to help detect and classify real ones in vast astronomical databases. These tools can spot the faintest of arcs, find symmetry that the human eye misses, and even predict shell orientation and age. In the near future, we may be able to map the entire shell galaxy population of the observable universe, and from it, reconstruct a rough but revealing timeline of galactic evolution. This would allow us to ask broader questions. How common are major mergers in the local universe? How does the frequency of shell galaxies change over cosmic time? Do certain galaxy types or environments favor shell formation more than others? The answers will help fill in the blanks of cosmic history, not with speculative theory, but with data carved into the heavens. Meanwhile, visual artists, astronomers, and educators alike are becoming captivated by the aesthetic potential of shell galaxies. Their haunting shapes evoke emotion, loneliness, transition, silence. Many public outreach campaigns have adopted shell galaxies as symbols of cosmic beauty, showing that science can be poetic without sacrificing rigor. In science fiction, too, shell galaxies are starting to appear as metaphors of collapsed civilizations, of ancient wars, of quiet alien legacies whose remnants float ghost-like across the void. And while these depictions are fictional, they reflect something profoundly true, that we project our own sense of time, loss, and memory onto the stars. Shell galaxies seem to carry that emotional resonance more than most astronomical phenomena. One can imagine an advanced alien race, looking at our Milky Way from afar, detecting faint arcs of light on its periphery, and deciphering from those structures the story of who we once collided with, and when. It's a reminder that galaxies, like civilizations, leave echoes. As we close in on the conclusion of this sprawling journey through shell galaxies, we return to the central idea that these structures are not simply beautiful, not just curious, they are essential. They are key pieces in the cosmic puzzle. They help us decode the dynamics of mergers, probe the nature of dark matter, challenge our understanding of gravity, and enrich our aesthetic and emotional connection to the universe. But perhaps their greatest gift is more personal. Shell galaxies remind us that even after the most violent changes, structure can return, beauty can emerge, and new forms can take shape from old ones. They are, in a cosmic sense, about resilience. When we look up and see those faint, elegant arcs spiraling out from a distant core, we're not just seeing light. We're seeing time, motion, memory. And in those shells, we catch a glimpse not only of galactic history, but of the universal truth that even in chaos, patterns arise. And so, as we peer deeper into the universe and uncover more examples of shell galaxies, we begin to realize that these structures aren't rare anomalies. They are silent chronicles of galactic life. Each arc, each ripple, each luminous shell etched into space is a snapshot of a transformation. Shell galaxies don't simply hint at the history of a galaxy. They are the history, laid out in ghostly layers, orbiting a center that has itself been reborn through merger and chaos. In their quiet persistence, shell galaxies present us with a paradox. They are made in violence, but they are graceful. They arise from gravitational fury, yet settle into forms that resemble echoes, waves, or musical notes, each shell tracing a contour of motion long since initiated. They suggest that even the most turbulent episodes in the universe's past can crystallize into order, and that memory in the cosmos is not stored in words or books, but in light and movement. The science of shell galaxies continues to evolve. Increasingly, astronomers are realizing that not all shells are alike, and their diversity holds new clues. Some shells are sharp and concentric, forming near-perfect circles. Others are warped, angular, or incomplete, suggesting more complex histories. Some galaxies show only 1 or 2 shells, while others exhibit as many as 20 or more, forming a cascading sequence like celestial tree rings. This morphological variation is more than cosmetic. It reflects the details of the merger event, the mass ratio of the two galaxies, the angle of infall, the orbital velocity, the degree of gas content, and even the presence of a galactic core or central black hole. And speaking of black holes, another layer of mystery unfolds. Some simulations suggest that major mergers, the kind that produce shell galaxies, can wake up dormant supermassive black holes. As gas is funneled toward the center of the post-merger galaxy, it can feed the black hole, triggering active galactic nucleus (AGN) activity, emitting powerful jets and radiation. Intriguingly, some shell galaxies have indeed been found to harbor AGNs, suggesting a possible connection between the birth of shells and the reawakening of a galaxy's core. This would mean that shell galaxies are not only beautiful and informative, they might also be dangerous. For any potential lifeforms orbiting within the host galaxy, a reignited black hole could irradiate entire regions, sterilizing star systems and altering planetary atmospheres. Shell formation, then, isn't just a structural event, it's a transformative event that reshapes the physical, chemical, and potentially biological environment of a galaxy. A single merger may change everything, from stellar population to galactic brightness, from star formation rate to life potential. Yet even as shells fade, their legacy endures. Over billions of years, the distinct arcs may dissolve into the background stellar halo, but astronomers have found that the memory of those shells is preserved in the motion of the stars. By studying stellar kinematics, how stars move within a galaxy, researchers can detect subtle patterns that betray past mergers. This means that even when the visual shells have vanished, their dynamical ghosts remain, like the footprints of dancers long after the music stops. We are also learning that the distribution of shells in a galaxy can be used as a tracer of the dark matter halo. Because the stars in the shells follow the gravitational potential of the entire galaxy, including its invisible dark matter component, the shell spacing and dynamics can help map the shape and mass of the dark matter halo. In some cases, this has revealed that dark matter halos are not spherical as once thought, but elongated or lopsided, reshaped by ancient galactic interactions. This blending of visible and invisible forces, of luminous arcs shaped by unseen mass, paints a picture of a universe that is not only more complex than we imagined, but more deeply interconnected. Shell galaxies are a bridge between what we can see and what we must infer, a fusion of light and shadow that reveals the contours of cosmic structure. Another remarkable angle is the connection between shell galaxies and ultra-diffuse galaxies, UDGs, a class of faint galaxies with large sizes but very low star densities. Some UDGs have recently been found with shell-like features, which raises intriguing possibilities. Could some UDGs be post-merger remnants that never fully recovered? Could their diffuse structure be the result of tidal stripping and shell formation, leaving behind a dim, ghost-like galaxy? This idea repositions shell galaxies within a broader taxonomy of galactic life. No longer are they just a footnote in elliptical galaxy evolution. They might be part of a spectrum of interaction outcomes, ranging from minor mergers that produce stellar streams, to major collisions that form shells, to complete absorptions that dissolve a galaxy into diffuse fog. Shells, in this framework, are just one expression of what happens when galaxies collide, a momentary configuration in the slow ballet of cosmic time. Yet for all we know, much remains unknown. There are shell systems we don't understand, patterns that defy simulation, structures that hint at multiple sequential mergers, or interactions involving non-galactic bodies like dark matter clumps or invisible companions. In rare cases, shells appear to exist without a clear cause, as though the galaxy is haunted by an event we cannot yet reconstruct. These outliers are tantalizing. They may be the key to unlocking new physics, or they may simply be products of unique histories we have yet to unravel. In either case, they remind us that shell galaxies are not a solved mystery. They are an ongoing puzzle, with pieces scattered across time and space, waiting for us to fit them together. And fitting them together is exactly what the next generation of space telescopes, AI-driven modeling platforms, and collaborative data efforts are striving to do. With instruments like the Nancy Grace Roman Space Telescope, deeper galactic imaging will soon become routine. What was once invisible will be cataloged, mapped, and compared across vast cosmological volumes. Entire populations of shell galaxies will be assembled, their diversity analyzed statistically, and their commonalities distilled into theory. But there's a humbling truth at the heart of this scientific effort: we are studying echoes. Every shell galaxy we observe is an artifact of something that happened long ago, sometimes billions of years in the past. The light we're seeing today began its journey before Earth had its first multicellular life. We're looking at ancient events through ancient light, and trying to reconstruct a dance that ended before our planet even had a name. In that way, shell galaxies aren't just about astronomy, they're about perspective. They force us to reckon with the vastness of time and the fragility of our moment within it. They show us that even the most stable-looking structures in the universe are transient, that permanence is an illusion, and that beauty often emerges only when the dust of disruption has settled. So the next time you look at an image of a shell galaxy, those ghostly arcs wrapped around a bright core, remember what you're seeing. Not just stars. Not just motion. But memory. Cosmic memory. The universe remembering what it once was, and quietly whispering its story through the language of light. And still, as we dive even deeper into the nature of shell galaxies, a larger existential question looms. What do these structures tell us about the ultimate fate of galaxies themselves? Are shells merely transitional features, or are they hints of how galaxies evolve toward a more diffuse, less structured end state? There's growing speculation that shell galaxies may represent a natural endpoint in the life cycle of many elliptical galaxies. As galaxies undergo merger after merger, their internal kinematics change. Ordered rotations give way to random, hot stellar motions, spiral structures dissolve, gas is stripped or consumed, and the galaxy becomes a spheroid of old stars. Shells are a visible punctuation mark in that evolutionary script, a residue of the last major act of transformation. In some models, the presence of shells coincides with the quenching of star formation, the moment a galaxy loses its ability to give birth to new stars, and begins its slow, quiet fade into cosmic senescence. This leads us into the territory of galactic archaeology, a term coined to describe the effort to reconstruct the history of galaxies by analyzing their structure, motion, and stellar populations. Shell galaxies are prime targets for this kind of research because their features can often be dated. The positions and curvature of the shells, combined with orbital mechanics, allow astronomers to estimate the time since the merger event that created them. In effect, each shell is a temporal marker, a ripple from the past that still moves through the present. Multiple shells in a single galaxy can even trace successive collisions, providing a layered timeline. One shell might be from a merger that happened 2 billion years ago, while another from a closer arc may mark a more recent event, just a few 100 million years old. No other galactic feature preserves time in quite this way. While spiral arms fade, dust lanes settle, and starbursts flare and die, shells remain, orbiting slowly like fossil rings of cosmic memory. One particularly rich area of research is the metallicity of the stars within shells. Because they often originate from smaller, less massive galaxies, the stars in the shells tend to be metal poor compared to the host galaxy. This difference allows astronomers to isolate shell populations spectroscopically and study their composition. By analyzing these chemical fingerprints, we learn not just when a merger occurred, but what kind of galaxy was absorbed. Was it a gas-rich dwarf galaxy? A metal-poor relic from the early universe? Or something even more exotic? The chemical story deepens when shells are found in galaxies that also contain globular clusters, ancient star clusters that are among the oldest known structures in the universe. In a few rare shell galaxies, some of these clusters appear to move in concert with the shells, suggesting they too were accreted during the same merger. This alignment of clusters and shells tells a richer tale, not just a collision, but the capture of an entire stellar ecosystem, complete with its own history and structure, folded into the identity of the host. In these cases, the host galaxy becomes a composite entity, a layered being formed from many predecessors, its light a blend of histories, its motion the sum of countless past gravitational arguments. It's almost poetic. Galaxies are not singular, but communal. They are made of others. They remember. This brings us to the even more speculative, but profoundly fascinating, frontier of dark galaxy interactions. Dark galaxies are hypothetical structures composed almost entirely of dark matter and little to no stars. They would be invisible in traditional telescopes, but their gravitational effects could still perturb visible galaxies. Some researchers have wondered, could certain unexplained shell structures arise from collisions with invisible companions? If this is true, it would mean shell galaxies could act as gravitational seismographs, reacting to encounters with dark matter-rich structures we can't otherwise detect. Their arcs and distortions could map out the gravitational shadows of the invisible universe. This would radically elevate the importance of shell galaxies, from mere merger remnants to tools for detecting the unseen architecture of the cosmos. Already, some strange shell-like asymmetries have been flagged by surveys like Pan-STARRS and DES, and they lack the expected stellar culprit. While these anomalies remain speculative, they hint at a broader role for shell dynamics in cosmology. In a universe where most of the mass is dark and unobservable, shell galaxies might be one of the few visible signs that something massive and hidden has passed through. And that brings us full circle. From humble star streams to elegant arcs, from merger echoes to dark matter probes, shell galaxies stretch across so many realms of astronomy that they feel almost mythological. They are beautiful, yes. But more than that, they are powerful tools, silent storytellers, and cosmic relics waiting to be read. One might even argue that in the future, as our observational capabilities reach further, perhaps through interferometry on the scale of entire solar systems or AI models trained on zettabytes of galactic data, shell galaxies will become not just subjects of study, but keys to entire epochs of cosmic history. We might map out not just local galactic mergers, but the complete collision history of the universe, shell by shell, arc by arc, loop by loop. In a way, the universe is writing its autobiography, and shell galaxies are its underlines, its emphasized moments, its dramatic turns. They are the punctuation marks in a narrative we are just beginning to translate. And in doing so, we find that space isn't empty, cold, or meaningless. It's full of echoes. Full of memory. Full of light sculpted by time. Shell galaxies are more than just remnants. They are testaments. They remind us that everything that exists leaves a trace, that even destruction can give rise to symmetry, and that in the aftermath of chaos, the cosmos sometimes whispers its deepest truths. And as we continue unfolding the story of shell galaxies, we realize their importance lies not just in their shape or their mystery, but in what they represent, the universality of change, the enduring signature of events that once seemed lost in time, and the sheer complexity of galactic ecosystems. In the grand cosmic theater, shell galaxies are among the most eloquent storytellers, not only chronicling the past but also hinting at the trajectories of the future. The more we study them, the clearer it becomes. Shell galaxies bridge the visible and the invisible, the past and the present, the ordered and the chaotic. They are born from interactions so vast and slow that they defy human timescales, yet the aftermath of those interactions creates structures that are stable and decipherable even billions of years later. It's like walking into an ancient ruin and being able to read the story of a lost civilization from the curvature of its walls. Now imagine, for a moment, what it would be like to live in a shell galaxy. The night sky would not just hold the usual scattering of stars. Depending on your location, You might see arcs of light encircling your sky, thin bands of densely packed stars that stretch across space like cosmic ribbons. To an intelligent species, these shells might become the focus of philosophical and scientific curiosity for millennia, appearing as vast, inexplicable rings, celestial scars or blessings, until, one day, their true nature is understood. Shell galaxies may even help redefine how we perceive the shape and identity of a galaxy. Traditional classifications like spiral, elliptical, and irregular are increasingly being viewed as incomplete or overly simplistic. Shell galaxies defy easy categorization. Some are lenticular in form, some are classified as elliptical, and yet others possess residual disk-like features. The presence of shells suggests that galaxy morphology is not a fixed identity, but a fluid result of environment, history, and interaction. What we call a galaxy is really just a phase, and the lines between these phases are blurred by events like mergers, starbursts, and yes, shell formation. Shell galaxies also open up an avenue to study the cold, diffuse stellar halos that surround many massive galaxies. These halos are among the most mysterious galactic components. They're dim, extended, and difficult to observe, yet they make up a large fraction of a galaxy's mass. Shells provide a way to illuminate the halo, to trace its shape and extent with arcs of captured stars. In some cases, shells have helped reveal that a galaxy's influence extends far beyond its bright central core, its gravitational dominion reaching hundreds of thousands of light-years into space. This leads to a crucial insight. Shell galaxies help map not just structure, but scale. They let us grasp the true size of galaxies, not by their light, but by their reach. In the same way that the rings of Saturn reveal the influence of its gravity, the shells of a galaxy reveal the extent to which it can shape and trap matter, even long after a merger has passed. And what about the role of gas? Interestingly, shell galaxies are often found to be gas-poor, particularly in the regions where shells form. This is not surprising, as many elliptical galaxies, especially those that host prominent shells, are already depleted of cold gas due to past star formation and heating events. However, in some systems, particularly those caught in intermediate stages of a merger, faint traces of neutral hydrogen and warm ionized gas have been detected near or around shell structures. These instances are rare, but they open up fascinating possibilities. Could some shells contain hidden star formation? Might the gravitational compression of accreted gas in shell regions trigger localized bursts of new stars? So far, evidence is limited, but as instruments improve, astronomers are keeping an eye on these anomalies. If confirmed, it would mean that shells are not merely remnants, but also cradles of new beginnings, acting as catalysts for rejuvenated star formation long after the collision itself. Moreover, there's potential in polar shell galaxies, a very rare subclass in which shells are aligned not around the major axis of the galaxy, but at more unusual, sometimes perpendicular orientations. These peculiar geometries may indicate multidirectional infall, where multiple satellite galaxies were accreted at different angles, or where a single merger was influenced by the triaxial nature of the galaxy's gravitational field. Polar shells suggest a greater complexity in galactic dynamics, and they challenge our assumptions about symmetry and structure. If shell galaxies are already rare, polar shell systems are the unicorns, astonishing, confounding, and deeply informative. From a cosmological perspective, studying shell galaxies can even aid in reconstructing the merger rate over time in the universe. By cataloging the number, age, and distribution of shell systems in large surveys, astronomers can estimate how frequently galaxies interacted and how those interactions evolved with cosmic time. Since shells fade after a few billion years, their presence gives a snapshot of recent merger history. In a way, shell galaxies are like tree rings of the universe, recording the seasons of its grandest collisions. This research has already revealed trends. Shell galaxies are more common at lower redshifts, i.e., in the nearby universe, and they seem to correlate with denser galactic environments. That is, you're more likely to find a shell galaxy near a galactic cluster or within a group, places where mergers are more likely to occur. In the early universe, violent and gas-rich mergers tended to produce starbursts and irregular galaxies. But as the universe aged, mergers became more dry and kinematically gentle, giving rise to these elegant shell formations. Looking ahead, the future of shell galaxy research is incredibly promising. Instruments like the Vera C. Rubin Observatory, formerly LSSD, will survey the sky in unprecedented depth and resolution, revealing thousands, perhaps millions, of shell structures previously hidden by distance or obscuration. At the same time, the James Webb Space Telescope and its successors will study their stellar populations in exquisite detail, unlocking the chemical and age profiles of individual shells. And with machine learning algorithms trained on simulated shell systems, astronomers will finally be able to reverse engineer merger events from observed shell patterns, turning each shell galaxy into a decoded chapter of cosmic evolution. And on a philosophical level, shell galaxies offer something that few cosmic phenomena can: a sense of closure. They are the postscript to violence, the symmetry that arises after chaos, the whisper of memory after the roar of creation. They are the universe's way of showing that every end leaves a trace, and that even the most catastrophic events can leave behind something elegant, quiet, and meaningful. In this light, studying shell galaxies becomes more than just an academic pursuit. It becomes a meditation on resilience, memory, and transformation. Just as galaxies absorb, reshape, and repurpose the fragments of their past, perhaps we, too, carry the echoes of everything we've endured, wrapped around us like cosmic shells, sometimes invisible, but always present. So the next time you look up at the night sky, imagine that far beyond what you can see, a galaxy is encircled by glowing arcs, remnants of something long past, still in motion, still beautiful. And in that, perhaps, lies the truest mystery of all. As we near the conceptual edge of our journey through the vast and elegant world of shell galaxies, it becomes increasingly clear that their story is not isolated. It is interwoven with the entire framework of galactic evolution, the unseen dynamics of dark matter, the behavior of stellar populations, and even the theoretical architectures that define the geometry of space-time. Shell galaxies are not just cosmic ornaments left over from ancient collisions. They are central to how the cosmos grows, adapts, and records its past. Consider how shell galaxies fit into the broader cosmic context of hierarchical galaxy formation, the prevailing model that suggests galaxies are not born fully formed, but rather assembled from smaller structures over time. In this framework, every galaxy we observe today is a composite, an amalgam of hundreds or even thousands of prior building blocks. Shell galaxies are among the clearest visual evidence for this model. When we observe shells, we are seeing the literal fossil record of that process. In fact, shell structures provide such powerful visual cues that they're often used as testing grounds for cosmological simulations. Computer models of large-scale structure formation, such as those performed in the illustrious Eagle or TNG cosmological simulations, reproduce shell galaxies as natural outcomes of minor and intermediate mergers. By comparing real shell systems to those generated in simulations, astrophysicists can test the accuracy of their assumptions about gravity, matter, dark matter, and cosmic expansion. This makes shell galaxies a kind of litmus test for our understanding of the universe. If we can accurately reproduce their structure, timing, composition, and frequency, we can be more confident that our models are on the right track. Conversely, any significant deviations between observed and simulated shell populations can indicate gaps in our understanding, perhaps in the distribution of dark matter, or in the efficiency of tidal disruption, or in how baryonic, normal, matter responds to violent collisions. And there are still plenty of gaps. For example, while most shell galaxies are explained by the radial merger model, some systems exhibit non-concentric shells, asymmetrical arcs, or ghost-like incomplete rings that don't fit neatly into the standard merger paradigm. These outliers force researchers to consider alternative scenarios. Could some shells result from gas inflows, feedback from active galactic nuclei, or interactions with larger-scale tidal fields in a galactic cluster? Adding further intrigue are the rare cases of multi-shell galaxies, those with dozens of concentric arcs stretching far into the galactic halo. The classic example is NGC 3923, which is known to contain more than 20 distinct shells. Such richness is difficult to explain with a single merger. Some theories suggest that these galaxies have undergone repeated, staggered mergers, each depositing a new layer of shells over cosmic time. Others posit a more continuous stream of minor accretions, slowly building up the shell pattern like ripples from overlapping raindrops. In this sense, shell galaxies aren't just snapshots of discrete events. They may be dynamic records of a galaxy's entire interaction history, layered like sedimentary rock in a canyon wall. Every shell, then, becomes an interface between time periods, each one preserving a moment when the galaxy was reshaped by an encounter. Another frontier in shell galaxy research involves the study of shell kinematics, the motion of stars within and across the shells. By using spectroscopy to measure Doppler shifts, astronomers can determine the velocity of stars within shells and compare them to predictions from merger models. This is a delicate, data-intensive task, as the stars and shells are spread thinly and often blend into the background halo. But when successful, these measurements reveal whether the stars are on circular, radial, or elliptical orbits, and whether the shells themselves are contracting, expanding, or remaining stable. So far, evidence suggests that many shells are kinematically cold, meaning their stars move along relatively ordered paths with low velocity dispersion. This is consistent with their origin from a coherent structure, like the disrupted core of a dwarf galaxy. In contrast, shells that are more chaotic in motion may indicate a more violent or multivectorial merger, or the interaction of the shell with an existing galactic structure like a rotating bar or triaxial halo. Interestingly, some shell galaxies have also been found to host low-luminosity active galactic nuclei, AGNs, supermassive black holes at their centers that are quietly accreting matter and emitting radiation. The presence of AGNs in shell galaxies may not be coincidental. Mergers can funnel gas toward the galactic center, feeding the black hole and temporarily igniting it. This offers a tantalizing connection between shell formation and black hole growth, one that's still being explored, but could reshape our understanding of feedback mechanisms in galaxy evolution. And as we think about growth, there's another connection worth highlighting: the relationship between shell galaxies and galactic cannibalism, a dramatic term for the slow absorption of smaller galaxies by larger ones. Shell galaxies are among the cleanest indicators of this process. While in some environments, galactic cannibalism produces warps, streams, or tails, in others it leaves behind a ghostly halo of arcs, barely visible yet perfectly preserved. This, once again, ties us back to a fundamental theme: shell galaxies as memories. They are the bones of past companions, orbiting like satellites long after their cores have vanished. They are graves, relics, and records, all in one. In the long view of cosmic time, every galaxy will likely become a shell galaxy. As the universe expands and interactions grow rarer, the remnants of past collisions will dominate the visual landscape of galaxies, faint arcs and halos glowing in the dark, reminders of a more turbulent age. In that distant future, perhaps billions of years from now, the universe will look quieter, colder, more fossilized. But within that silence, the shells will still whisper. And what they whisper is this: the universe does not forget. Every collision leaves a curve. Every encounter leaves a line. Every ending leaves a circle. The deeper we look, the more we find these stories layered upon stories, each one carved in light and motion, each one waiting to be read. Shell galaxies are not anomalies. They are the punctuation of existence, the commas, the parentheses, and sometimes the final period at the end of a cosmic sentence. They are the closest thing we have to written history in space, and in every arc, we glimpse not just the structure of a galaxy, but the very shape of time. And so, in the glowing crescents scattered across the void, we read the past, contemplate the present, and perhaps even foresee the shape of what is to come. And as we draw nearer to the heart of this cosmic enigma, the role of shell galaxies as not only passive recorders but active participants in galactic evolution becomes increasingly apparent. They don't simply reflect the past, they influence the future. Their formation alters the gravitational dynamics of their host galaxies, reshapes star distributions, and may even trigger secondary processes like gas inflows, starburst episodes, and central black hole activity. The gravitational potential of a galaxy is altered with each merger. As the structure changes, so does the behavior of orbiting stars, gas, and dark matter. Shells, though composed of stars that were often once part of smaller satellite galaxies, redistribute the mass profile of the host system. In this way, shells subtly reshape the galaxy's rotation curve and velocity dispersion profile. These effects, although faint and difficult to detect, are critical for understanding the mass-to-light ratios in shell galaxies, and by extension, their dark matter content. Indeed, one of the most fascinating uses of shell galaxies lies in the indirect measurement of dark matter halos. Since the stars in the shells orbit the galaxy according to its total gravitational potential, both visible and invisible, they act as tracers of the underlying mass distribution. By mapping the geometry and spacing of the shells, astronomers can infer the shape and density of the galaxy's dark matter halo. Is it spherical? Flattened? Triaxial? Shells are among the few visible structures that can provide answers. Studies have shown that the radii at which shells appear, and the velocity of stars within them, do not always correspond to what would be expected from baryonic matter alone. This mismatch strongly implies the presence of a massive dark matter halo. In some cases, this method has been used to rule out certain alternative theories of gravity that attempt to explain galactic dynamics without invoking dark matter. In essence, shell galaxies help affirm the dark matter hypothesis by serving as celestial seismographs of hidden mass. But there's more. Beyond dark matter, shell galaxies are beginning to play a surprising role in the study of modified gravity theories, especially those that seek to challenge or expand upon Newtonian dynamics at large scales. Some modified gravity models predict shell structures that differ subtly in formation timing, spatial distribution, or kinematic behavior from those predicted by standard models. By comparing real-world shell galaxies to the predictions of these models, physicists can test the limits of our understanding of gravity itself. This elevates shell galaxies to a status few expected, not merely oddities or relics, but potential probes of fundamental physics. And yet, even as shell galaxies serve as tools for theory, they remain deeply aesthetic objects, visually poetic, hauntingly symmetrical, and embedded with natural beauty. There's something almost eerie about their silence. In photographs captured by deep sky surveys, they appear as luminous ripples in the blackness, concentric halos gently hugging a central spheroid. Unlike spiral arms or galactic bars, which pulse with motion and color, shells are often monochrome, faint, and static, frozen echoes of motion long since dissipated. Some astronomers have likened them to cosmic fossils, while others see them as the onion skins of a galaxy's soul. They lack the chaotic violence of collisional rings or the grandeur of spirals, but in their restraint lies an almost meditative elegance. To look at a shell galaxy is to look at cosmic patience, the long, slow ballet of gravitational orbits that take hundreds of millions of years to form and just as long to fade. And fade they do. One of the most underappreciated aspects of shell galaxies is their impermanence. Over time, the stars within shells slowly diffuse. Their coherent structure erodes as stars interact gravitationally with the rest of the galaxy, with giant molecular clouds, or with each other. Shells that are bright and well-defined today may be barely detectable a billion years from now. This gives shell galaxies a fleeting quality, a reminder that even the most ordered cosmic structures are transient. In fact, some astrophysicists suspect that many galaxies which appear smooth and unremarkable today may have once been glorious shell galaxies, now scrubbed clean by entropy. All that remains is a subtle hint in the stellar population, a mild excess in radial star count, or a vague asymmetry in the halo. The shells are gone, but their fingerprints remain. This is yet another way in which shell galaxies remind us of the cyclical nature of cosmic evolution. It also poses a challenge to observers. If shell galaxies are temporary, how many have we already missed? What percentage of galaxies we classify as normal ellipticals, or lenticulars, once wore shimmering rings of light? The only way to answer this is with deeper, more sensitive surveys, and those are coming. Instruments like Euclid, JWST, and eventually the Nancy Grace Roman Space Telescope will pierce further into galactic halos, revealing ever fainter shells and resurrecting the pasts of seemingly quiet galaxies. Perhaps, then, shell galaxies are not rare in the absolute sense. Perhaps they are only rare in the present moment. Like comets, they shine for a time, then vanish into the background. Their lives are long by human standards, but brief on cosmic timescales. What we are witnessing in every shell galaxy is a phase in a much longer story, a transitional moment in the eternal remixing of the universe's structure. And as we understand this, the narrative of shell galaxies becomes deeply human. These cosmic shells echo the same themes found in our own lives: emergence from conflict, layering of experience, evolution from chaos toward stability. They remind us that identity is fluid, shaped by what we absorb, what we lose, and what we remember. Shell galaxies, in this metaphor, are not just stellar remnants. They are monuments to transformation. They show us how even the most disruptive forces can leave behind beauty. How violence can give way to harmony. How galaxies, like people, can carry the shape of their past without being defined solely by it. And so, as we scan the skies for new shells, hidden in data, waiting in archives, shimmering faintly at the edges of known systems, we are not just looking for patterns in stars. We are listening for stories in the dark. Stories of collision, of survival, of rebirth. Stories that may yet change how we understand the cosmos. Because shell galaxies are more than just phenomena. They are questions wrapped in light, and they are still waiting to be answered. But even as we marvel at the majestic arcs and luminous edges of shell galaxies, there's a whisper of something even more profound, what we don't yet understand. For all the models, observations, and simulations, shell galaxies still harbor mysteries that challenge our deepest assumptions about how galaxies grow, interact, and evolve. One of the most compelling open questions is the true frequency and distribution of shell galaxies throughout the cosmos. While they are more commonly found in elliptical and lenticular galaxies, especially in relatively low-density environments such as galaxy groups and field regions, they are notably underrepresented in dense galaxy clusters. This suggests that shell structures are fragile and likely to be disrupted by the chaotic gravitational interactions common in those crowded regions. But it may also hint at a bias in our observational capabilities. After all, the faintest shells are incredibly difficult to detect against the complex background of cluster light. Newer techniques, such as deep learning algorithms trained to find low surface brightness features in vast sky surveys, are already beginning to change this picture. Projects like Galaxy Zoo and initiatives using the Dark Energy Survey or HSCSSB, Hyper-SupremCam Subaru Strategic Program, have helped identify previously unnoticed shell galaxies, hidden in plain sight. The application of AI-enhanced data mining has not only increased the number of known shells but also unveiled unusual morphologies, such as nested shells within shells, or asymmetric arcs with irregular spacing that don't fit neatly into established categories. Some of these strange cases challenge the prevailing notion that most shells are formed by radial, minor mergers. Could there be other mechanisms at work? What if some shells are not remnants of past galaxies at all, but are gravitational wave echoes, relics of interaction with exotic dark matter structures, or the imprints of cosmic strings slicing through galactic halos? While these ideas remain highly speculative, they are actively discussed in theoretical circles as the universe continues to reveal structures that don't always conform to standard expectations. Moreover, recent theoretical work has proposed that shell galaxies may serve as sensitive detectors for galactic tides and intergalactic currents. Just as sand patterns on a beach can reveal the motion of tides, so too might the detailed geometry of shell galaxies reflect subtle gravitational influences exerted by nearby galaxies or larger-scale structures. For example, simulations show that if a shell galaxy lies within the gravitational potential well of a larger group or filament, its shells may appear twisted, warped, or stretched depending on the direction of that external influence. In this way, shell galaxies could be used as cosmic weather vanes, pointing the way toward invisible gravitational fields that would otherwise remain undetectable. These gravitational currents could help map the large-scale structure of the universe with greater fidelity than redshift surveys alone, especially when combined with weak lensing data and cosmic microwave background fluctuations. And then there is the strange case of shell galaxies with gas. Traditionally, shell galaxies are seen as dry mergers, collisions between galaxies with little to no interstellar gas. But in a handful of documented cases, such as NGC 474, shell galaxies exhibit traces of neutral hydrogen, Hi, or even molecular gas. In extremely rare examples, they may even contain young stellar populations, suggesting that star formation is, or was, occurring within or near the shell structures themselves. This raises the intriguing possibility that not all shell galaxies are built from ancient, gas-per collisions. Some may form through wet mergers, or interactions involving gas-rich dwarfs, which could create hybrid systems, shell galaxies with embedded stellar nurseries. This is a radical departure from the classical image of shells as static, fossilized remains. It implies that shell galaxies might not just preserve the past, they might shape the future, by igniting new waves of star formation triggered by the accretion process. Even more exotic is the potential connection between shell galaxies and ultra-diffuse galaxies, UDGs. UDGs are strange, ghostly galaxies with the size of the Milky Way but only 1% of its stars. Some theories suggest that UDGs may be the stripped cores of former shell galaxies, or vice versa, that UDGs absorbed smaller satellites and began developing shell-like structures that eventually dispersed. This theory has not been conclusively proven, but it points to a possible evolutionary relationship between two of the most enigmatic types of galaxies in the universe. Another tantalizing mystery involves globular clusters. These ancient stellar systems orbit galaxies like satellites, and are believed to form during early galactic assembly. But what if some globular clusters, especially those on radial orbits, are the leftovers of past shell-forming events? If a dwarf galaxy with its own globular clusters is consumed during a merger, the clusters may be flung outward and continue to orbit the host galaxy independently. By studying the orbital distribution of globular clusters, astronomers may be able to trace the historical shell-forming events of the galaxy they now surround. All of this points to one inescapable truth: shell galaxies are not just rare curiosities. They are integral to understanding galactic archaeology, cosmic structure, and the physics of deep time. And the deeper we go, the more their story evolves, from simple structures formed by gravitational tides to multifaceted laboratories for studying dark matter, gravity, star formation, black hole fueling, and cosmic evolution. They are bridges between epochs. Time machines made of light. Sculptures carved by collision. As future telescopes like the Extremely Large Telescope, ELT, 30-meter telescope, TMT, and LUVOIR come online in the coming decades, we will be able to probe the outskirts of galaxies in unprecedented detail. These new tools will extend our reach into the low-surface brightness regime, allowing us to see shells fainter and farther than ever before. We may discover that shell galaxies are not rare at all, but that our previous technological limits blinded us to their full prevalence. Eventually, we may be able to trace entire shell histories, reconstructing how a galaxy has grown through time, merger by merger, ripple by ripple. With these advances, we will no longer look at a shell galaxy and simply ask, "What caused this?" Instead, we will ask, "How many lives has this galaxy lived?" Shell galaxies are not the end of the story. They are the beginning of a new kind of cosmic storytelling, one told not in bursts of radiation or galactic collisions alone, but in the slow, graceful arcs of stars sweeping through space in elegant formation. Every shell is a sentence. Every arc is a phrase. And we are only just beginning to read the language of galaxies written across the sky. To truly appreciate the cosmic elegance of shell galaxies, one must step back and consider the philosophical implications of their existence. Unlike many of the violent, dynamic, and high-energy phenomena in the universe, shell galaxies whisper rather than shout. They do not blaze like quasars, collapse like neutron stars, or explode like supernovae. Instead, they unfold quietly over billions of years, like ripples in a cosmic pond, created by the delicate interplay of gravity, motion, and memory. Their very structure is a memory imprint, a frozen echo of a gravitational past, playing out over scales of time so vast that human intuition falters in the face of it. Each concentric arc, each faint loop, tells a tale not just of galactic merger, but of persistence. the persistence of stars that have survived the tidal dismemberment of their former host, the persistence of patterns that refuse to blur into randomness, the persistence of gravity as a sculptor, working with a chisel made of time. And if we dare to interpret these arcs as memories, then we begin to see shell galaxies as cosmic journals, written not in ink but in starlight. Galaxies that have encountered others, absorbed them, and worn their remnants not with shame but with quiet dignity. These are not ruins in the traditional sense, they are evolved states, beautiful and solemn. It's also deeply humbling. When we observe a shell galaxy, we are seeing not just what is, but what was. We are looking at a message sent hundreds of millions of years ago. A message formed when our own planet was young, when dinosaurs may have still walked Earth, or even before. Shell galaxies are messengers from an ancient epoch, their structures shaped long before humanity ever peered into the night sky. In this sense, they are also cosmic mirrors. We, too, are shaped by forces we do not fully understand. Our identities are built layer upon layer, shaped by external encounters, internal evolution, and the hidden scaffolding of memory. Just as galaxies grow through the accretion of smaller bodies, we grow through the accumulation of experience, some joyful, some traumatic, all transformative. The shells of a galaxy are like the layers of human history, or the rings of a tree, evidence of passage, of survival, of change. Shell galaxies show us that even in a universe governed by entropy and decay, there is also structure and poetry. That even after violence, after collision and consumption, beauty can emerge. Not in the perfection of symmetry, but in the elegance of scars. And the scars of shell galaxies are truly cosmic. Some reach tens or even hundreds of kiloparsecs from the galactic center. Some fade into the intergalactic dark, barely distinguishable from the cosmic background. Others are sharp and luminous, standing in clear contrast to the core, glowing like rings of memory wrapped around a beating heart. In the future, we may learn to use shell galaxies not just as historical tools or astrophysical laboratories but as navigational instruments, guides to charting the evolution of galaxy groups, clusters, and even large-scale cosmic filaments. As more are discovered in different stages of formation, across different cosmic epochs, a more complete timeline will emerge, perhaps one that could tie into the formation of the cosmic web itself. Some theorists have even proposed that dark matter interactions could produce shell-like artifacts under certain conditions, especially if dark matter has complex self-interacting properties. In such scenarios, shell structures could be one of the few indirect signals of these exotic interactions. Imagine, shells not from stars, but from dark matter itself. A dark shell galaxy would be almost invisible, but its gravitational fingerprint, when overlaid with baryonic tracers, could one day reveal the architecture of an unseen universe layered beneath our own. It may sound fantastical, but this is the very frontier where astrophysics meets imagination. As our tools grow more sensitive, and our models more sophisticated, what once seemed like the edge of knowledge becomes the beginning of a new chapter. And speaking of chapters, the story of shell galaxies is still being written. At this very moment, as we stare into telescopes or examine survey data, new shell galaxies are being formed. Somewhere in the depths of space, a dwarf galaxy is approaching a massive elliptical, spiraling inward on a fatal orbit. In a few million years, it will be shredded, its stars sent ricocheting through the halo of its host. In another billion years, those stars will slow, bunch together, and form the gentle arcs of a new shell. A new page in the universal record. We may not live to see its completion, but we are witnessing the process begin. And perhaps, someday, intelligent beings elsewhere in the universe will study our own galaxy and find faint shell-like structures on its outskirts. They'll ask the same questions we ask now: what caused this? When did it happen? What does it tell us about the past? Because ultimately, shell galaxies are about the inheritance of structure, a concept that echoes through science, philosophy, and even human culture. What we build, what we endure, and what we leave behind becomes part of a larger whole. The universe, too, remembers. And so, as we continue to study shell galaxies, not as isolated oddities but as vital characters in the ongoing story of the cosmos, we begin to shift our perspective. We stop seeing the universe as static and cold, and begin to understand it as a living history, shaped by motion, marked by time, and illuminated by the faint glow of ancient stars. Shell galaxies are not only scientific puzzles, they are cosmic testimonies. Proof that the universe not only creates, but remembers. Even as we delve deeper into the enigma of shell galaxies, the horizon of unanswered questions continues to expand. One of the most compelling mysteries is how shell structures evolve over time. Are they permanent? Do they fade? Do they collapse back into the host galaxy? Or do they remain as long-term relics in the galactic halo? Simulations suggest that shell systems are transient, often surviving for a few billion years before being stretched into obscurity by the host galaxy's gravitational field. But this duration depends on the orbital properties of the accreted galaxy, the mass and shape of the host's dark matter halo, and the inclination of the incoming satellite's trajectory. Some shells vanish more quickly than others, their visibility a fleeting window. Others may linger in ghostly stillness, marking the galaxy's outskirts like a pale halo of time. Recent work has shown that shells evolve differently depending on whether the encounter is prograde, in the direction of the host galaxy's rotation, or retrograde, against it. Prograde encounters tend to result in more symmetric and concentrated shells, while retrograde ones often create asymmetric, scattered structures that decay faster. This opens up a fascinating line of investigation. By analyzing the distribution and orientation of shells, we might reconstruct not just the history of mergers, but the directional memory of galactic interactions, essentially turning the shells into a three-dimensional kinematic fossil record. There's also the mystery of shell multiplicity. Some shell galaxies have just a few faint arcs, while others display dozens of intricate rings, like the growth lines of an ancient tree. Does this reflect multiple sequential mergers? Or can a single event produce multiple layers over time? In some cases, it appears that a single satellite galaxy on a radial orbit can create a long train of shells simply through repeated passes through the host's core. Each pass deposits new stars that fan out to form a distinct shell, like ripples from a skipped stone across a pond. But these models don't always match observation. Some shell galaxies display chaotic or broken arcs, some with misaligned symmetry axes, or shells that appear to rotate relative to the central structure. These anomalies hint at complex gravitational perturbations, possibly from secondary mergers, hidden satellite companions, or triaxial halo effects that twist the stellar orbits over time. In this way, each shell system becomes not just a snapshot but a dynamical puzzle, a 4D record of galactic history that incorporates space, time, and motion. And here's another curiosity. Why are shells predominantly seen in elliptical and lenticular galaxies, but almost never in spirals? Is this simply a selection effect, because spiral arms and dust obscure faint structures? Or is it something deeper? Perhaps ellipticals are more likely to undergo the dry, radial mergers necessary to produce visible shells? Spirals, with their rotational support and rich interstellar gas, may simply respond differently to the same merger events, generating tidal tails, warps, or starbursts instead of shells. Yet, this general rule has its exceptions. A few spiral shell galaxies have been discovered, such as NGC 3310, which exhibits faint shell-like arcs amidst its starburst activity. These rare examples suggest a more complex interplay between gas dynamics, disk stability, and stellar feedback in shaping post-merger features. It challenges the neat classification of galaxies and urges us to think in spectrums, not silos. In fact, shells themselves might not be limited to just the optical regime. In multi-wavelength observations, astronomers have begun searching for infrared or ultraviolet counterparts to known stellar shells. While most shells are composed of old stars, some appear to contain younger populations, particularly in galaxies that still retain a bit of cold gas after merging. Ultraviolet imaging from galaxies has revealed faint UV arcs in a few shell systems, possibly tracing intermediate-age star formation from enriched tidal debris. Similarly, radio telescopes like ALMA and MEERKAT have probed shell galaxies for neutral hydrogen, HI, and molecular gas. In rare instances, a thin veil of gas has been found draped along the stellar arcs, indicating that gas, normally thought to disperse rapidly during dry mergers, might sometimes be retained or reacquired, especially in group environments. This opens up fascinating possibilities about secondary accretion, where shell galaxies capture gas from their surroundings and potentially reignite star formation, becoming something between a fossil and a phoenix. And then there's the gravitational unknown, shell galaxies and dark matter. One of the most compelling uses of shells is to trace the mass distribution of their host galaxy's dark matter halo. Because the shell stars move through the halo under gravity alone, their distribution can serve as a probe of the underlying potential. By modeling how shells form and where they appear, astronomers can test different models of dark matter halos, spherical versus triaxial, cuspy versus chord, and even exotic models involving self-interacting dark matter. In particular, the spacing of shells can reveal the mass profile of the host galaxy. If the halo is more massive, stars will decelerate faster and produce closer, more frequent shells. Conversely, in lower mass halos, shells will be more widely spaced. This method, though still being refined, offers a non-lensing based technique to map dark matter, an incredibly valuable tool, especially at intermediate redshifts where gravitational lensing becomes more difficult to apply directly. But let's take this a step further. Could shell galaxies themselves be used as cosmological probes? There's growing interest in using statistical properties of shell galaxies, such as frequency, morphology, alignment, and environment, as a cosmic chronometer to trace how galaxies grow over cosmic time. In the early universe, mergers were more frequent and more chaotic. As the universe aged, it cooled and became more structured, with fewer major collisions. Thus, the abundance and characteristics of shell galaxies at different redshifts could provide a fossil record of merger history, complementing other techniques like galaxy luminosity functions, clustering statistics, or redshift surveys. Already, surveys like COSMOS, CANDELS, and JWST deep fields are beginning to detect shell-like features in high redshift galaxies, an astonishing discovery, given the faintness and angular resolution required. These early shells may be different in shape and size, reflecting the more turbulent conditions of early galaxy assembly. If confirmed, they could extend the timeline of shell galaxy formation all the way back to the cosmic noon, the peak of star formation and galaxy interactions roughly 10 billion years ago. Imagine that, a faint arc of stars, over 10 billion years old, tracing a forgotten collision in a galaxy that no longer exists. Light that began its journey before Earth even formed, now arriving at our telescopes as a glowing memory. That's the wonder of shell galaxies. They are not just stellar ornaments or gravitational echoes. They are cosmic storytellers. And the stories they tell, of violence, integration, memory, and persistence, are some of the most compelling narratives in the universe. Yet the more we learn about shell galaxies, the more elusive their full meaning becomes. They seem to exist in a paradox, visibly subtle yet cosmically significant, fragile in appearance but forged from galactic collisions. To understand them completely is to grasp something fundamental about the nature of cosmic transformation, about how galaxies evolve not in isolation, but through encounters that leave behind luminous scars. At the forefront of this research is the ever-growing contribution of machine learning and artificial intelligence. As astronomical surveys collect terabytes upon terabytes of data from telescopes around the world and in orbit, it has become nearly impossible for humans to visually scan every galaxy image for shell-like structures. To solve this, astrophysicists are now training convolutional neural networks and deep learning systems to recognize the faint patterns of shells in galaxy surveys, even when buried beneath noise, background stars, or distorted shapes. These algorithms, once refined, will enable astronomers to uncover thousands of previously undetected shell galaxies, many in environments or configurations that defy our expectations. Some early results from AI-powered surveys have already revealed shell galaxies and galaxy clusters, where gravitational tides from neighboring galaxies or the cluster itself may play a role in triggering or warping shell formation. Others have hinted at asymmetric or one-sided shell structures, suggesting unconventional merger geometries or ongoing environmental interactions. The implications of these findings are profound. As more shell galaxies are discovered, patterns begin to emerge, correlations with galaxy luminosity, local density, halo mass, and stellar age populations. We begin to trace the demographics of shell formation, just as one might map the rise and fall of civilizations in ancient history. Where once shell galaxies were treated as isolated oddities, they now form a statistical ensemble, offering not just individual stories, but a cosmic census of galactic memory. And with this broader view comes deeper questions. Could shell galaxies form not just from mergers, but from resonant interactions, where stars in the halo are disturbed by passing satellites or even dark subhalos, clumps of dark matter with no luminous counterpart? Simulations suggest that dark matter substructure in a galaxy's halo could, under the right conditions, induce shell-like patterns by disturbing the orbits of stars in the outskirts. If so, then the shells we see might be partly shaped by invisible actors, their arcs outlining the gravitational presence of something we cannot directly observe. Alternatively, consider the role of galactic bars and triaxial potentials, non-spherical distortions in the gravitational field of the host galaxy. These can shepherd stars into resonant orbits, causing shell-like features to appear even without mergers. Such secular shells might look similar to those caused by accretion events, but originate from internal dynamical evolution rather than external collisions. If both mechanisms can create shell-like structures, then distinguishing between them becomes a crucial task, one that will require not just imaging, but spectroscopy, kinematics, and time-domain modeling. Instruments like the European Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, will soon provide the resolution and sensitivity to probe these questions in stunning detail. Using integral field spectroscopy, astronomers will be able to map the motions of stars in and around shell structures, identifying whether they follow radial or circular orbits, how they differ in age or metallicity from the host galaxy, and what these differences imply about their origin. And then there's JWST, the James Webb Space Telescope, offering unprecedented views of distant galaxies in the near-infrared. Though not optimized for wide surveys, JWST's deep imaging capabilities may uncover shell galaxies at higher redshifts than ever before, especially those with faint stellar halos too dim for ground-based telescopes to detect. These could represent proto-shell galaxies, just beginning to form their arcs in the aftermath of early universe mergers. Finding such systems would provide a direct window into the onset of shell formation in cosmic history. Meanwhile, the Vera C. Rubin Observatory and its Legacy Survey of Space and Time, LSST, will soon scan the entire southern sky repeatedly over 10 years, capturing the dynamic evolution of countless galaxies, including those with changing or emerging shell structures. Though shell galaxies evolve on long timescales, LSST might catch variability in surrounding structures, subtle stellar migrations, or even supernovae within shells, allowing us to piece together the life cycles of these outer halos. Perhaps the most exciting future development is the creation of a global shell galaxy catalog, a comprehensive, machine-curated, human-verified atlas of every known shell system, complete with metadata on morphology, color, redshift, environment, and inferred merger history. This would allow scientists to trace correlations across tens of thousands of shell galaxies and test cosmological predictions with unprecedented power. With such a dataset, we could begin asking bold questions. Are shell galaxies more common in filamentary structures of the cosmic web, where galaxy interactions are more frequent? Do certain cosmic epochs show peaks in shell formation, reflecting phases of accelerated galactic growth? Can shells be used to constrain the properties of dark energy, by tracing how merger rates evolve with cosmic expansion? Could shell patterns someday help identify anomalous physics, like deviations from Newtonian gravity or evidence of fifth forces? These aren't idle speculations. As our observational power increases, the structures that once seemed marginal become central to our understanding of cosmic history. Just as fossilized leaves and rock tell us about ancient climates, shell galaxies may offer the fossils of galactic dynamics, preserved not in stone, but in light. Even more speculatively, some researchers have proposed that technosignatures, traces of advanced extraterrestrial civilizations, might someday be inferred from anomalous shell structures. While no credible evidence of this exists today, The idea is that a civilization capable of manipulating stars on galactic scales, as in the concept of a Kardashev Type 3 civilization, might leave behind non-natural stellar arcs, shell-like features that defy gravitational modeling. In such a case, shells could become not just tools for astrophysics, but for astroarchaeology on a galactic scale. And this brings us full circle to the idea of shell galaxies as storytellers. They don't just describe gravitational events. They narrate a larger theme, that in a universe governed by entropy and chaos, patterns can still emerge. That memory, though scattered among stars and warped by time, can endure. That the cosmos is not silent, it is full of stories etched into its very structure, waiting for us to listen. Each shell is a sentence. Each galaxy a paragraph. The universe, a novel written across space-time. And we, fortunate readers, are just beginning to turn its pages. As we continue to explore the vast canvas of shell galaxies, a new layer of depth begins to emerge, the connection between shell systems and the broader philosophy of cosmic time. While science often addresses the mechanics, how shells form, what they mean dynamically, what information they carry, their deeper resonance touches something more profound. They are chronograms of destruction and rebirth, written not in ink, but in starlight. They are the slow ripples of a forgotten encounter, expanding silently through a galactic ocean that remembers more than it reveals. This metaphor of memory is not merely poetic, it reflects the thermodynamic persistence of shell structures. Unlike spiral arms or star-forming regions, which can fluctuate quickly and change shape in relatively short cosmic spans, shells have no internal feedback mechanisms. They are not driven by gas dynamics or stellar winds. Instead, they are created by gravity alone. They form slowly, evolve slowly, and vanish slowly, if at all. In this sense, they are perhaps the purest expression of collision-induced structure in the universe. They do not shine brightly. They do not move fast. But their very stillness is what makes them so revealing. Now imagine extending this idea beyond individual galaxies. Could we envision a metastructure of shells, a kind of cosmic archaeology across clusters or superclusters? In theory, if galaxies within a cluster frequently interact, something expected in dense environments like the Coma cluster or the Virgo cluster, they could give rise to multiple shell systems with overlapping features. These could, in the far future, create a shell web, where the arcs of different galaxies overlap and interfere, creating a cosmic palimpsest of interactions. Although we are not yet technologically equipped to map such large-scale faint structures in high detail, this idea motivates new forms of deep field observation. Telescopes optimized for low-surface brightness imaging, such as the Dragonfly telephoto array or future instruments built on similar optical principles, could begin to detect the faintest edges of these arcs, ones that are currently invisible against the noise of our instruments. And it is precisely this threshold of detectability that forms one of the biggest barriers and opportunities in shell galaxy research. Shells are not just visually faint, they are mathematically faint in the sense that they push the limits of signal processing, data cleaning, and feature extraction. Much like gravitational waves, which required the invention of new kinds of measurement strategies before we could hear them, shell galaxies may require an entirely new observational philosophy, to focus not on the bright centers of galaxies, but on the silent peripheries, where structure hides in the whisper of starlight. Beyond our own Milky Way, scientists speculate whether our galaxy may harbor ancient shell remnants, fossils of long-forgotten mergers that occurred billions of years ago. Due to our position inside the disk and the overwhelming brightness of the galactic center and bulge, it is extremely difficult to detect such structures from within. However, surveys like Gaia have already detected stellar streams and coherent overdensities in the halo, structures that may, under different orbital conditions, have evolved into shell-like features. And here lies another critical realization: shells and streams are cousins, born of the same gravitational drama but shaped by differing initial conditions. Streams form when satellite galaxies are shredded over many orbits, leaving behind long trailing filaments. Shells form when the satellite plunges deeply and quickly into the host, its stars released in bursts, fanning out into shells. Understanding this family of tidal features, shells, streams, fans, rings, is like learning the different dialects of galactic interaction. Each has its own syntax, its own cadence, its own way of telling time. And just like dialects, some shell systems are rare and exotic. Astronomers have classified various subtypes: Type 1 shell galaxies, with symmetric, interleaved shells aligned along the major axis of the host; Type 2, with randomly placed or spiral-like arcs; and Type 3, which are disordered or chaotic. These classifications help guide the modeling process, but they also suggest a spectrum of formation histories, each shell system potentially shaped by its own blend of mass ratios, orbital angles, and encounter speeds. But could there be undiscovered types of shell galaxies? Possibly even entire populations that we are blind to due to our current methods? For instance, shell galaxies seen edge-on might show arcs that are compressed or blurred, appearing as simple lensing-like distortions. Others may be mistaken for tidal features, ring galaxies, or disturbed ellipticals. This means the universe may contain far more shell galaxies than we've catalogued, perhaps even orders of magnitude more. That realization is what continues to fuel efforts to refine our simulations, using increasingly sophisticated models that include not just stars and dark matter, but gas, feedback, star formation, chemical enrichment, and magnetic fields. The goal isn't simply to create more realistic shells, it's to embed shells within a larger galactic ecosystem, and understand how they co-evolve with their hosts, their companions, and the universe at large. As we simulate and observe more shell galaxies, a strange theme emerges. They seem to appear during moments of galactic transformation. Not just mergers, but identity shifts, a spiral becoming an elliptical, a dwarf being subsumed, a group becoming a single dominant galaxy. In a way, shells are markers of galactic turning points, boundary layers between what a galaxy was and what it will become. And there's something poetic in that. Because when we step back and look at the arc of human curiosity, we see a similar pattern. Like stars in a shell, we too are scattered across time, our knowledge expanding outward, orbiting truth, falling back, reforming. Each time we make a discovery, it sends ripples into our understanding. And occasionally, when the light catches just right, we see the faint arcs of insight, the shells of our own progress, radiating from the impact of wonder. In this sense, shell galaxies don't just teach us about space. They reflect something deeper. That time leaves its mark. That collisions create change. That memory, cosmic, stellar, or human, is never truly lost, only scattered. And every arc in the sky reminds us, there is always more to uncover. And so the journey into the realm of shell galaxies continues, not just as a scientific pursuit, but as an exploration of the very mechanisms by which the universe remembers its past. These faint arcs of stellar debris, luminous yet fragile, are physical imprints of time itself, preserved across millions, sometimes billions of years. They are the aftermath of cosmic encounters that didn't just reshape individual galaxies, but transformed the dynamics of entire systems, leaving behind structures that defy simple categorization. One fascinating thread emerging from ongoing research is the relationship between shell galaxies and elliptical galaxy evolution. For decades, elliptical galaxies were considered old, dead systems with little star formation and relatively simple histories. But the discovery of shell structures in otherwise undisturbed ellipticals suggests that many of these systems have complex, merger-driven pasts. Some even contain shells aligned in intricate patterns, almost like fossilized ripples in a pond, a clear indicator that the galaxies have ingested smaller companions within the last few billion years. This has led to a broader rethinking of how early-type galaxies evolve. No longer are they viewed as static endpoints of galaxy evolution. Rather, they are active participants in hierarchical assembly, growing through repeated accretion events. In this light, shell galaxies offer critical evidence for the bottom-up structure formation model. The idea that small galaxies formed first and merged over time to create larger, more massive systems. In simulations that incorporate this cosmological framework, shell formation appears not as an anomaly, but as a natural consequence of galactic growth. As small satellite galaxies fall into larger host halos, they often pass through the central regions on radial orbits, getting tidally disrupted and releasing stars that settle into phase-wrapped shells. Depending on the mass ratio of the merger, the number of passages, and the orbital orientation, a variety of shell morphologies can result. But shells aren't just relics of the past. They can also inform us about the present-day distribution of dark matter. Because stars and shell structures are essentially test particles, moving in the host galaxy's potential, their dynamics encode information about the shape and strength of the gravitational field. By carefully measuring the spacing, symmetry, and velocity distribution of shells, astronomers can infer properties of the dark matter halo, including its ellipticity, density profile, and even possible anisotropies. This is where shell galaxies become more than visual curiosities. They become astrophysical laboratories. Just as gravitational lensing can be used to map dark matter around massive clusters, shell systems provide an independent method for constraining the mass distribution in individual galaxies. In fact, a few studies have suggested that certain shell configurations can only be reproduced if the host's dark matter halo has a triaxial, or even lopsided shape, challenging traditional assumptions about dark matter symmetry. In some simulations, shell formation appears sensitive to the timing of halo assembly. For example, galaxies that acquired the bulk of their mass early in cosmic history might form shells that are smoother and more symmetric, whereas late-forming systems might exhibit distorted or incomplete arcs, possibly due to ongoing interactions with other satellites, or a still-settling halo. These differences provide indirect clues about the timing and dynamics of structure formation on galactic scales. Furthermore, the chemical composition of shell stars offers another dimension of analysis. Since these stars originate in a disrupted satellite galaxy, their metallicity and elemental abundances may differ from the host's native population. Spectroscopic studies have confirmed that some shells are enriched in alpha elements, suggesting they formed from systems that experienced rapid star formation before being assimilated. This opens the door to galactic archaeology, allowing researchers to reconstruct the star formation history and chemical evolution of long-dead satellites through the fossil record of their debris. But perhaps the most exciting frontier lies ahead, in the potential discovery of shell-like structures in the early universe. While shells are faint and difficult to detect, upcoming facilities like the Nancy Grace Roman Space Telescope and even successors to JWST may have the sensitivity to identify shell features in galaxies billions of light-years away, seen as they were shortly after the Big Bang. If shells can be observed at such high redshifts, it would indicate that minor mergers were already shaping galaxy morphology very early on, challenging current timelines for hierarchical growth. Additionally, the question of whether shells can form in disk galaxies is gaining traction. Traditionally, shell galaxies have been associated with elliptical or lenticular systems, where stars can move in a variety of orbital directions. However, some simulations suggest that under the right conditions, particularly if the infalling satellite is aligned with the host's disk plane, ring-like or arc-like features resembling shells can emerge even in spiral galaxies. These might be confused with resonant rings or spiral arms, but subtle kinematic differences could reveal their true origin. And then there are the shell galaxies that defy explanation. Systems where the arcs are offset from the center, or where shells appear on only one side. These are the rebels. Test cases that challenge our assumptions, force us to refine our models, and sometimes expose the limits of our understanding. Each of these galaxies is a puzzle, a cosmic question mark hanging in the void. The ultimate hope is that by solving these puzzles, we might one day construct a unified theory of tidal structures, a framework that explains not just shells, but streams, plumes, bridges, and fans, all as outcomes of the same basic gravitational processes. This would be a major step toward a holistic understanding of galaxy assembly, and the invisible scaffolding of dark matter that guides it. Until then, shell galaxies remain a frontier. A beautiful, silent frontier illuminated not by fireworks, but by echoes of long-lost galaxies, long-set collisions, and long-forgotten dances of stars. They are the universe's quiet memory, flickering on the edge of visibility, always waiting to be read by those who know how to listen. And as we press further into the mystery of shell galaxies, a new question surfaces, one not of shape or structure, but of sequence. What happens after the shells form? Do they dissipate into the galactic background, gradually blending into the main body of the galaxy? Do they remain indefinitely, like long echoes in a cavern of stars? Or can they trigger further galactic evolution, serving as more than just relics of a collision but as catalysts for what follows? The truth is more complex and, in many ways, more intriguing. Though shell structures are composed of stars, not gas, they can have indirect consequences on galactic evolution by perturbing the gravitational equilibrium of their host. In galaxies where gas is still present, perhaps in an elliptical that has not yet fully quenched star formation or in a gas-rich merger remnant, the formation of shell structures can induce radial mixing, potentially stirring up gas that had otherwise settled into stable orbits. This can occasionally trigger new star formation episodes, though these are rare and usually weak compared to those in classical spirals. But there's a more subtle, far-reaching effect that shell formation can have. They affect angular momentum redistribution. When a satellite galaxy falls into a host and sheds its stars into shells, it doesn't just deposit mass, it alters the angular momentum profile of the host galaxy. This redistribution can lead to kinematic decoupling in the galaxy's central region, even forming counter-rotating cores or peculiar velocity dispersions that persist long after the shells fade. These kinematic signatures are crucial, because they're often easier to detect than the faint shells themselves, offering a powerful proxy for ancient interactions that no longer leave visible debris. Moreover, shell systems can evolve internally. The classic ripple pattern, concentric arcs, may slowly smooth out due to phase mixing, a process where the orbits of stars become desynchronized over time. In simulations, we see that well-ordered shells can degrade into faint, diffuse halos, meaning that some elliptical galaxies with no visible shell structure today may once have hosted brilliant arcs. This makes shell systems temporally asymmetric. They are clearest shortly after formation, but increasingly elusive as time moves forward. This gradual fading raises another compelling possibility, that shell galaxies may be a transitional phase in galaxy morphology. Just as post-merger galaxies can evolve into ellipticals, and irregulars can settle into spirals, shell galaxies might represent a morphological waypoint, a brief window in which the violent history of a merger is still imprinted in the stars, before being washed away by time. In that sense, every shell galaxy we observe is a snapshot of galactic healing, a wound still visible before it scars over. As observational tools improve, astronomers have begun to detect asymmetries in many shell systems, signatures that suggest more than one merger or a non-uniform disruption process. Some galaxies exhibit shells that do not align with any single axis or have varying surface brightness from arc to arc. This may indicate multiphase accretion, where multiple dwarf galaxies were absorbed over a period of time. In these cases, shells overlap and interfere like waveforms, creating a complex superstructure of stellar debris, an astronomical palimpsest. To understand these complex systems, scientists are now turning to machine learning. By training neural networks on simulated shell galaxies, researchers can identify subtle features that may be invisible to the human eye or buried in noise. Early results show promise. AI can recover faint shells even in edge-on systems or highly contaminated backgrounds. Eventually, we may deploy autonomous systems to scan deep sky surveys and catalog hidden shell galaxies by the thousands, revealing patterns no one thought to look for. But the most extraordinary applications may come from cross-domain analysis, comparing shell systems across different wavelengths. While optical light reveals stars, infrared imaging can expose older, cooler populations, and X-ray observations might reveal traces of hot gas stirred up by the merger. Some shell galaxies even show faint radio halos, hinting at past AGN activity potentially triggered by the infall of a satellite galaxy. This suggests a possible feedback loop. A small galaxy crashes in, forms shells, destabilizes gas near the core, fuels a central black hole, and launches an outburst that then influences the surrounding galactic halo. This interplay of gravitational dynamics, gas physics, and AGN feedback presents a multi-layered narrative, where shells are not just inert features, but active participants in cosmic evolution. They may be faint, but their implications are immense. Some researchers are even asking a radical question: Could shell galaxies be used as standard clocks of cosmic time? If the formation of shell systems follows predictable orbital mechanics, and if the spacing between shells truly reflects the time since the original merger, then in principle, we could reverse engineer shell structures to date galactic collisions across the cosmos. Like reading tree rings in a fallen log, we'd be reconstructing the timeline of events not from motion, but from geometry. It's still a speculative idea, but it opens up exciting possibilities. Especially when we consider that many shell galaxies are not isolated, they exist in groups, clusters, and even filamentary environments. If we can link shell systems to the dynamics of their local environments, we could use them to map gravitational interactions across cosmic filaments, perhaps even infer the hidden paths of dark matter flows. Shell galaxies, in that way, become time-space compasses, tools for understanding the flow of mass, energy, and entropy in the universe on both local and large scales. It is also worth considering their cultural and philosophical symbolism. To the untrained eye, shells appear fragile, random, almost accidental. But to the astrophysicist, each arc is a trace of precision, a deterministic echo governed by Newtonian mechanics and cosmic gravity. In this duality, of chaos and order, we find a mirror of our own human condition. We, too, are shaped by collisions. We, too, leave behind faint traces of encounters that altered our trajectories forever. And like galaxies, we orbit things we barely understand. Shell galaxies remind us that not all beauty in the universe is flamboyant. Some of it is quiet. Some of it lives in the margins, in the faintest strokes of stellar debris painted on the edge of night. Some beauty can only be seen by those who go looking for the invisible. And yet once you see it, it's impossible to forget. The beauty of shell galaxies, then, lies not just in their astronomical significance, but in their very subtlety. Unlike the dynamic, star-forming spirals or the intense, supermassive elliptical galaxies, shell galaxies communicate in whispers. Their faint arcs speak volumes about the violent cosmic dance they have witnessed, but they do so in a language that takes time to decode. And as we decode these whispers, we uncover not just the histories of individual galaxies, but the larger narrative of cosmic evolution, one that spans billions of years and involves countless interactions between galaxies, stars, and dark matter. In a very real sense, shell galaxies offer a window into the early stages of galactic mergers. Most galaxies we observe today have passed through multiple merger events in their history, yet the process is often hidden from view due to the intense activity that tends to obscure the aftermath. But shell galaxies allow us to study a snapshot of the galactic evolutionary process when the effects of mergers are still visible, before they fade away into the more settled structures we see in the present-day universe. As more and more shell galaxies are discovered, we begin to realize just how widespread and diverse they are. Shell galaxies are not rare anomalies confined to isolated regions of space. They are found in various environments, from galaxy clusters to the cosmic voids, indicating that the processes that lead to their formation are likely universal. This has profound implications for our understanding of galaxy formation and evolution. By studying shell galaxies, we can begin to understand the common threads that run through the complex and varied ways in which galaxies grow and evolve across the universe. Moreover, as technology advances, the tools we use to study these galaxies are becoming increasingly sophisticated. The development of next-generation telescopes, including ground-based observatories like the European Extremely Large Telescope, ELT, and space-based missions such as the James Webb Space Telescope, JWST, will likely provide us with unprecedented levels of detail. With these instruments, we will be able to probe not only the structural features of shell galaxies, but also their internal kinematics, stellar populations, and even the distribution of dark matter that governs their gravitational interactions. The ongoing development of advanced simulations also holds promise for deepening our understanding of shell galaxies. These computer models can simulate the intricate gravitational forces at play during galaxy mergers, shedding light on how these interactions give rise to the shells we observe today. They can also help us understand the broader implications of shell formation, such as the influence of dark matter and the role of galaxy environments in shaping the structure of these systems. While current models suggest that shell formation is primarily a result of minor mergers, ongoing research continues to refine our understanding of the process. The latest studies indicate that the specific conditions needed for shell formation might involve a delicate balance of factors, including the mass of the satellite galaxy, its orbital parameters, and the properties of the host galaxy. In some cases, it seems that the geometry of the merger, how the satellite galaxy is oriented relative to the host galaxy's center, plays a key role in determining the size, shape, and number of shells formed. This makes shell formation a more complicated process than previously thought, with many variables influencing the final outcome. It is also worth noting that not all shell galaxies behave in the same way. While many exhibit smooth, symmetrical rings or arcs, others show asymmetrical structures, with some shells appearing more elongated or irregular. These differences may be a result of the varying mass ratios between the merging galaxies, the orbital dynamics of the satellite galaxy, or even the presence of additional environmental factors, such as gravitational interactions with neighboring galaxies or the tidal influence of a nearby galaxy cluster. As a result, shell galaxies come in all shapes and sizes, each with its own unique story to tell. Some may be relics of ancient mergers that occurred billions of years ago, while others may still be undergoing the slow process of merger evolution, their shells gradually becoming more diffuse over time. Some shell galaxies may even be in the process of merging with a larger, more massive galaxy, with their shells gradually fading into the background as the host galaxy continues to grow and evolve. Understanding this diversity is critical for unlocking the full potential of shell galaxies as tools for studying the broader universe. By comparing different types of shell galaxies, astronomers can gain insights into the different phases of galactic evolution, as well as the varied ways in which galaxies interact with one another. This comparison will also shed light on the role of mergers in the formation of galaxies, a key question that has long been central to the field of astrophysics. But beyond their scientific value, shell galaxies also invite a sense of wonder and awe. When we look at these structures, faint arcs of stars stretching out into the void, we are not just seeing remnants of ancient cosmic collisions. We are also glimpsing the profound beauty of the universe's intricate and ongoing processes. These galaxies, though seemingly distant and detached from our everyday experience, remind us of the infinite scale and complexity of the cosmos. They are a testament to the dynamic nature of the universe, constantly evolving and changing. As new stars are born, old stars die, and galaxies collide and merge in an endless cosmic dance. In a way, shell galaxies are a metaphor for the broader journey of exploration and discovery. Much like these faint arcs of stars, the process of understanding the universe is often a slow, incremental effort. We begin with only the faintest of clues, fragments of evidence scattered across vast distances, and slowly, over time, piece together a more complete picture of the cosmos. And just as the shells of stars stretch out into the distant reaches of space, our knowledge of the universe is constantly expanding, pushing the boundaries of what we know and uncovering new mysteries along the way. Shell galaxies are more than just astronomical objects. They are a reminder of the fragility and impermanence of all things. Just as the shells they form will eventually fade into the background, so too will the stars that once shone brightly within them. And yet, even in their fading, they leave behind a legacy, a trace of cosmic history that will be studied and admired by generations of astronomers yet to come. For now, we are left to contemplate these elusive remnants of the universe's past. We gaze upon them not as a final answer, but as a question that continues to beckon us into the cosmos, urging us to uncover the hidden forces that shape the galaxies around us. And as we continue to study shell galaxies, we will undoubtedly learn more about the universe than we ever thought possible, one faint arc at a time. As we delve deeper into the study of shell galaxies, one aspect that continually fascinates astronomers is the relationship between these structures and the elusive nature of dark matter. Dark matter, an invisible and enigmatic substance thought to make up approximately 27% of the universe's mass energy content, plays a pivotal role in the formation and evolution of galaxies. While dark matter itself does not emit, absorb, or reflect light, its gravitational influence is fundamental to the behavior of visible matter, stars, gas, and dust, in galaxies. Understanding how shell galaxies form and evolve offers a unique opportunity to study the underlying dark matter halos that envelop these cosmic structures. The creation of shells depends heavily on the gravitational potential well of the host galaxy, which is largely determined by the distribution of dark matter. When a smaller satellite galaxy falls into this potential, its stars are stripped and spread out along specific orbits, creating the shell patterns we observe. These orbits are influenced by the shape and depth of the dark matter halo, meaning that the arrangement of shells can provide indirect clues about the invisible scaffolding supporting the galaxy. Studies using high-resolution simulations have shown that the geometry and spacing of shells are sensitive to the dark matter halo's shape. For example, a more spherical halo tends to produce symmetric shell systems, while elongated or triaxial halos can lead to asymmetric, warped shell structures. By comparing observational data of shell galaxies to these simulations, astronomers can infer the properties of their dark matter halos with unprecedented precision. This methodology allows for a kind of cosmic cartography, mapping dark matter in ways that are otherwise impossible. Moreover, shell galaxies serve as natural laboratories for testing models of dark matter itself. Various theories propose different characteristics for dark matter particles, ranging from cold, collisionless particles to self-interacting dark matter or even fuzzy, wave-like dark matter. Each model predicts subtle differences in the gravitational behavior of halos, which in turn affect how shells form and persist. Observing discrepancies between expected shell configurations and actual observations could provide critical insights into the fundamental nature of dark matter, potentially guiding physicists closer to identifying its true identity. Beyond dark matter, the study of shell galaxies intersects intriguingly with the phenomena of supermassive black holes, SMBHs. Most massive galaxies harbor SMBHs at their centers, and their growth and activity are closely linked with galactic mergers, the very events that produce shell structures. When a satellite galaxy merges with a larger host, it can funnel gas toward the central SMBH, igniting energetic phenomena such as quasars or active galactic nuclei, AGN. Those shell galaxies often appear quiescent, some display signs of past or ongoing AGN activity, hinting at a profound connection between the merging process and the feeding of these cosmic giants. Furthermore, the kinematic signatures left behind by shell formation may impact the accretion dynamics around SMBHs. The gravitational perturbations caused by shells can alter the flow of gas in the central regions, influencing how material is drawn into the black hole's sphere of influence. Studying these effects can shed light on the feedback mechanisms regulating galaxy growth and black hole activity, topics that remain at the forefront of astrophysical research. On a larger scale, shell galaxies offer clues about the hierarchical assembly of cosmic structures. The universe's large-scale structure is shaped by the gradual buildup of matter through successive mergers, from small dwarfs to massive clusters. Each shell galaxy encapsulates a snapshot of this process, reflecting the layered history of accretion events that shaped it. By cataloging shell galaxies across different environments and epochs, astronomers can reconstruct the timeline and pattern of cosmic growth, providing empirical constraints for cosmological simulations. The challenge, however, lies in detecting and analyzing these faint structures. Shells are often extremely low in surface brightness, requiring sensitive instruments and deep imaging to observe. Advances in observational astronomy, including wide-field surveys and deep imaging techniques, are gradually overcoming these obstacles. Projects such as the Legacy Survey of Space and Time, LSST, at the Vera-C. Rubin Observatory promise to revolutionize our understanding by unveiling countless shell galaxies with exquisite detail, enabling large-scale statistical studies that were previously impossible. In addition to optical observations, multi-wavelength approaches enrich our knowledge of shell galaxies. Infrared surveys penetrate dust-obscured regions, revealing older stellar populations, while radio observations can detect synchrotron emission associated with AGN activity or past merger shocks. X-ray telescopes provide insight into hot gas halos and potential feedback effects. Integrating these datasets offers a holistic view of shell galaxies, illuminating the interplay between stars, gas, black holes, and dark matter. Looking forward, the synergy between observations, simulations, and theory will deepen our grasp of shell galaxies. Machine learning and artificial intelligence are poised to accelerate discovery by automating the identification of shell features across vast datasets. These technologies can detect subtle patterns and classify shell systems based on their morphology and kinematics, uncovering trends and anomalies that might otherwise escape human analysis. In the grand tapestry of the cosmos, shell galaxies stand out as testaments to the dynamic and ever-changing nature of the universe. They are the cosmic ripples formed by the gravitational waves of mergers, the fingerprints of interactions that shaped galaxies across time. Studying them is not just about cataloging pretty arcs in space, it is about unraveling the deep history of matter, energy, and the fundamental forces that govern all existence. As our instruments grow more powerful and our understanding more nuanced, shell galaxies will continue to illuminate the dark corners of the universe. They remind us that even in the vast emptiness of space, history is written in the stars, in the delicate shells that arc silently around distant galaxies, whispering stories of cosmic collisions and the inexorable flow of time. Beyond their scientific importance, shell galaxies also capture the imagination as celestial artworks sculpted by the forces of gravity. Their graceful, concentric arcs evoke the image of ripples on a pond, frozen in cosmic time, a visual metaphor for the lasting effects of galactic encounters. But while the beauty is undeniable, the physics behind these shells reveals the immense complexity of the universe's large-scale dynamics. One particularly intriguing aspect is the time scale over which shell galaxies evolve. The shells themselves are not permanent fixtures. Rather, they are transient features that can persist for hundreds of millions to a few billion years. Over these vast spans of time, the stars comprising the shells gradually disperse and merge with the general stellar population of the host galaxy, causing the shells to fade from view. This ephemeral nature means that the shells we observe today offer a glimpse into relatively recent merger events in cosmic terms, events that might have occurred well after the initial formation of the galaxy. This raises interesting questions about how frequently such mergers occur. Galactic mergers are a fundamental aspect of the hierarchical formation model of the universe, where small structures merge to form larger ones. Shell galaxies, by their very nature, indicate that minor mergers are relatively common and that their signatures can last long enough for astronomers to detect and analyze them. However, the visibility of shells depends on factors such as the mass ratio of the merging galaxies, the orbital parameters, and the age of the merger. Consequently, the detection of shell systems can be used to estimate merger rates in the local universe, offering constraints on galaxy formation theories. Another fascinating inquiry involves the composition of stars within the shells. Are these stars predominantly from the disrupted satellite galaxy, or does the merger process trigger new star formation within the shells? Observations suggest that most shell stars are old and metal-poor, indicating their origin in smaller, less evolved satellite galaxies. This contrasts with the host galaxy's typically more metal-rich and older stellar population. Detailed spectroscopic studies allow astronomers to examine the chemical composition and ages of shell stars, shedding light on the merger history and the evolutionary status of the satellite galaxies involved. In some shell galaxies, however, signs of recent star formation have been detected, suggesting that the merger can compress gas and ignite bursts of new stars along the shell structures. These star-forming shells are relatively rare and may depend on the presence of sufficient cold gas in the merging galaxies. Such findings provide a link between shell formation and the broader processes of star formation and galactic evolution. The role of environment in shaping shell galaxies is also a subject of ongoing research. Shell galaxies have been found in various cosmic settings, from isolated galaxies in the field to densely packed galaxy clusters. The environmental density can influence the frequency and type of interactions a galaxy experiences. In clusters, for example, gravitational interactions with multiple neighbors and the hot intracluster medium may affect the survival and visibility of shells. Understanding how environment impacts shell formation and longevity helps to contextualize these galaxies within the larger cosmic web. As technology advances, astronomers are also beginning to detect shell-like structures in other wavelengths beyond the visible spectrum. Ultraviolet observations can highlight young stars and recent star formation in shells, while radio emissions may reveal interactions with surrounding gas and magnetic fields. Infrared observations help to penetrate dust and study the older stellar populations in greater detail. This multi-wavelength approach enriches our understanding of the complex physical processes at play. Shell galaxies also connect intriguingly to the study of stellar dynamics and orbital mechanics on galactic scales. The stars forming the shells typically move along highly elliptical orbits, reaching apocenters that trace out the shell edges. By studying the velocities and distributions of these stars, astronomers gain insights into the gravitational potential of the host galaxy. This in turn informs models of galaxy mass distribution, including the elusive dark matter halo. Moreover, shell galaxies have inspired theoretical advancements in galaxy interaction modeling. Early models considered simple radial infall scenarios, but modern simulations incorporate more realistic, complex orbital configurations, including angular momentum, orbital eccentricity, and the three-dimensional structure of galaxies. These improvements allow for more accurate predictions of shell shapes, brightness profiles, and evolution. Despite decades of study, many mysteries about shell galaxies remain. For instance, the exact mechanisms determining the variety of shell morphologies, such as the differences between concentric shells, interleaved arcs, and more chaotic structures, are still under investigation. Additionally, the influence of factors like the presence of multiple satellite galaxies or the role of gas dynamics complicate the picture further. These unanswered questions make shell galaxies a dynamic and exciting field of study, bridging observational astronomy, computational physics, and cosmology. Each new discovery and technological breakthrough adds pieces to the puzzle, gradually illuminating the rich tapestry of galactic history and the ongoing evolution of the universe. Shell galaxies are more than mere curiosities. They are key witnesses to the dramatic and transformative events that shape galaxies across cosmic time. Their faint, ghostly arcs tell stories of ancient collisions, gravitational dances, and the complex interplay of dark matter and visible stars. As we continue to explore and understand these enigmatic structures, shell galaxies will remain at the forefront of our quest to decipher the universe's grand narrative, offering profound insights into the forces that have sculpted the cosmos as we see it today. Peering further into the depths of shell galaxies, we find that their study extends beyond understanding individual galactic encounters and into the realm of cosmic archaeology. Just as archaeologists on Earth sift through layers of soil to uncover traces of past civilizations, astronomers analyze shell galaxies to uncover the layers of cosmic history written in stars and stellar debris. Each shell, each ripple, is a fossil record of a past galactic event, capturing moments when gravity reshaped vast swaths of matter on unimaginable scales. A particularly compelling avenue of research is the age dating of shells. By measuring the positions, velocities, and stellar populations within shells, astronomers can estimate when the merger that created them occurred. These time frames can range from a few 100 million years to over 1 billion years ago. Such age estimates allow researchers to correlate shell formation events with other galactic phenomena, such as bursts of star formation, changes in galactic morphology, or the triggering of active galactic nuclei. This correlation helps build a comprehensive timeline of how galaxies grow and transform over cosmic time. Furthermore, shell galaxies serve as a testing ground for fundamental physics on large scales. The gravitational interactions that produce shells operate under the laws of Newtonian gravity and general relativity but occur in environments where dark matter dominates. Observations of shell dynamics and morphology can be used to test alternative theories of gravity, such as modified Newtonian dynamics, MOND, which propose changes to gravitational laws to explain galaxy rotation curves without invoking dark matter. By comparing the predictions of these theories with observed shell structures, astronomers can assess their validity, contributing to the ongoing debate about the nature of gravity and dark matter. In addition, the faintness and subtlety of shell galaxies highlight the challenges of observational astronomy. Many shells are so diffuse that they remain undetected even in deep surveys, meaning that the population of known shell galaxies likely represents just a fraction of those actually existing in the universe. Advances in instrumentation, Data processing techniques and dedicated surveys are essential to unveiling these hidden structures. Innovative methods like surface brightness fluctuation analysis, stacking techniques that combine data from multiple observations, and machine learning algorithms designed to identify low-contrast features are pushing the boundaries of what is visible. The discovery of shell galaxies beyond our local universe adds another dimension to their study. Observing these systems at higher redshifts, meaning looking back in time, can reveal how the frequency and characteristics of mergers have changed over billions of years. This cosmological perspective helps place shell galaxies within the larger framework of galaxy evolution and the growth of cosmic structure since the early universe. On the theoretical side, the interplay between hydrodynamics and stellar dynamics during mergers is an area ripe for exploration. While stars are collisionless particles that respond primarily to gravity, gas behaves differently. It can shock, cool, and form new stars. How gas dynamics influence shell formation, whether they help dissipate energy and sharpen shells or cause shells to become more diffuse, remains an open question. Incorporating realistic gas physics into simulations promises a more complete understanding of shell galaxies and the star formation triggered by mergers. The human aspect of studying shell galaxies should not be overlooked. The quest to understand these structures involves a global community of astronomers, engineers, and data scientists working collaboratively across continents and disciplines. Large observational campaigns require the coordination of multiple telescopes, spanning optical, infrared, radio, and X-ray wavelengths. Meanwhile, theorists develop complex simulations requiring cutting-edge supercomputing resources. This collective effort embodies the spirit of scientific inquiry, pushing the boundaries of knowledge through shared curiosity and technological innovation. Shell galaxies also inspire cultural and philosophical reflection. Their existence reminds us that the universe is a place of constant change, where even seemingly stable structures like galaxies are shaped by dramatic, sometimes violent events. The faint shells tracing ancient mergers evoke a sense of cosmic impermanence and interconnectedness, illustrating how the universe's grand design is crafted from countless interactions over unimaginable timescales. In the era of upcoming astronomical facilities, such as the Extremely Large Telescope, ELT, the 30-meter telescope, TMT, and next-generation space observatories, the study of shell galaxies will enter a new golden age. These instruments will provide unprecedented spatial resolution and sensitivity, allowing detailed dissection of shell structures, stellar populations, and dynamics in ways previously impossible. Combined with advances in computational modeling, these observations will refine our understanding of the merger processes and their impact on galactic evolution. Shell galaxies stand as silent witnesses to the ever-changing cosmos, their delicate arcs narrating stories of encounters, mergers, and transformations that shape the universe. They bridge the gap between the visible and invisible, the past and present, and the known and unknown. Through them, we glimpse the dynamic artistry of gravity and time, a cosmic dance that continues to sculpt the heavens. As our gaze deepens and our tools sharpen, the secrets held within these ethereal structures will continue to unfold, enriching our understanding of the universe and our place within it. Building upon the profound insights gleaned from shell galaxies, it is essential to consider their role within the broader context of galaxy morphology and classification. Galaxies have long been categorized based on their shape and structure: ellipticals, spirals, lenticulars, and irregulars. Shell galaxies predominantly belong to the category of elliptical and lenticular galaxies, which are generally characterized by older stellar populations, a lack of significant gas and dust, and relatively smooth, featureless appearances. The presence of shells disrupts this simplicity, revealing a more tumultuous and active past than their smooth exteriors might suggest. This dichotomy highlights how shell galaxies serve as vital clues to the evolutionary pathways of elliptical galaxies. Traditionally, elliptical galaxies were thought to form through the rapid, violent collapse of gas clouds in the early universe, or through major mergers of similarly sized galaxies. However, the widespread existence of shells points toward the importance of minor mergers and accretion events in their ongoing evolution. These smaller, less dramatic collisions leave behind subtle, layered signatures such as shells, which slowly fade over time but testify to a galaxy's cannibalistic history. The shells themselves are diverse in form and complexity, often categorized into three main types based on their morphology. Type 1 shells are aligned concentrically and symmetrically around the galaxy center. Type 2 shells are irregular and asymmetrical, and Type 3 shells are more chaotic and fragmented. This classification helps astronomers link the observed shell features to the underlying physics and orbital dynamics of the merger events that created them. For instance, symmetric shells often indicate nearly radial infall of the satellite galaxy, while asymmetric shells suggest more complex orbital geometries. Another fascinating dimension to shell galaxy studies is the role of stellar streams and tidal debris that often accompany shells. When galaxies merge, stars are torn away, creating long, thin streams of stars, remnants of the disrupted satellite's orbit around the host galaxy. These stellar streams, observed in our own Milky Way as well as in distant galaxies, complement the shell structures and offer additional clues about merger histories. Together, shells and streams form a coherent picture of how galaxies grow by consuming smaller companions. In the Milky Way, for example, ongoing accretion events have been detected through stellar streams such as the Sagittarius stream, demonstrating that our galaxy, too, is shaped by these processes. While the Milky Way does not prominently display shell structures, likely due to differences in merger history and galactic environment, it exemplifies the broader cosmic principle that galaxies are dynamic, evolving systems influenced by continual accretion. The study of shell galaxies also intersects with the quest to understand galaxy quenching, the process by which star formation ceases in galaxies, leading them to become red and dead. Many shell galaxies are found to be quiescent, lacking significant star formation. This raises questions about whether minor mergers contribute to quenching by heating or stripping gas, or conversely, whether they can trigger bursts of star formation that temporarily rejuvenate galaxies. Understanding this balance is key to unraveling how galaxies transition between active and passive phases. From a cosmological perspective, shell galaxies provide a window into the mass assembly history of galaxies across cosmic time. By comparing nearby shell galaxies with those observed at greater distances, and thus earlier epochs, astronomers can trace how merger rates and mechanisms evolve. Current evidence suggests that minor mergers were more frequent in the past, contributing significantly to the growth of massive galaxies. Shells, therefore, act as cosmic signposts marking this evolutionary journey. The synthesis of observational data, theoretical modeling, and simulations is crucial to advancing shell galaxy research. Cutting-edge cosmological simulations, such as Illustris and Eagle, incorporate complex physics to model galaxy formation and evolution in a cosmological context. These simulations reproduce shell-like features and merger remnants, allowing for direct comparison with observations. Discrepancies between simulated and observed shells prompt refinements in modeling galaxy interactions, dark matter properties, and feedback processes. In recent years, the advent of integral field spectroscopy has revolutionized the study of shell galaxies. This technique captures spatially resolved spectra, enabling astronomers to map the motions, chemical compositions, and ages of stars across the shell structures. Such detailed information reveals the kinematic and stellar population gradients within shells, offering insights into the merger dynamics and the nature of the progenitor galaxies. Furthermore, ongoing and future deep sky surveys will dramatically increase the known population of shell galaxies, enabling statistical analyses that can discern trends related to galaxy mass, environment, and cosmic time. The synergy between large surveys and detailed follow-up observations will build a comprehensive framework for understanding these captivating objects. On the frontier of discovery, astronomers are exploring the possibility that shells may also be associated with exotic phenomena, such as the presence of intermediate-mass black holes within the disrupted satellites, or interactions involving dark matter substructures. These areas remain speculative but highlight the rich potential for shell galaxy studies to uncover new physics. Shell galaxies embody the intricate interplay between structure and evolution in the cosmos. They reveal that galaxies are not static islands but dynamic entities shaped by ongoing interactions, mergers, and accretions. The shells are the delicate echoes of these processes, etched into the fabric of space and time, awaiting our discovery. Through their study, we deepen our understanding of how the universe builds complexity from simplicity, and how the grand cosmic dance of matter unfolds over billions of years. The exploration of shell galaxies continues to be a vibrant and evolving field, promising fresh insights and surprises as we develop new tools and push the boundaries of astronomical knowledge. As we gaze at these ethereal shells, we are reminded of the universe's vastness, its history written in stars, and our own small yet profound quest to comprehend the cosmos. Diving even deeper into the mysteries surrounding shell galaxies, one cannot overlook the intriguing connection these structures have with the elusive nature of dark matter halos enveloping galaxies. Dark matter, which does not emit, absorb, or reflect light, remains undetectable through direct electromagnetic observation, yet its gravitational influence is essential to explaining the motions and structures observed in galaxies and clusters. Shell galaxies offer a unique opportunity to probe these unseen halos because the stars forming shells trace the gravitational potential in exquisite detail. When a smaller satellite galaxy falls into a larger host, its stars are stripped and spread out along orbits dictated by the combined gravitational field of the host's visible matter and its dark matter halo. The shape, spacing, and velocity distribution of shells depend heavily on this potential. By comparing observed shell patterns with simulations that vary the properties of the dark matter halo, such as its mass, shape, spherical or triaxial, and concentration, astronomers can infer the distribution of dark matter in the host galaxy. This method provides a valuable complementary approach to other dark matter probes, such as galaxy rotation curves or gravitational lensing. The triaxiality of dark matter halos, meaning they are not perfectly spherical but elongated in different directions, can create asymmetric and more complex shell morphologies. Observations of shell asymmetries thus potentially offer direct evidence of the three-dimensional shape of dark matter halos, an otherwise challenging measurement. This insight helps refine our understanding of dark matter's role in galaxy formation and evolution. Beyond dark matter, shell galaxies also intersect with the study of supermassive black holes, SMBHs, residing in the centers of massive galaxies. Major mergers are known to fuel the growth of these black holes by funneling gas toward the nucleus. Minor mergers, which create shells, might also contribute to SMBH growth by delivering fresh material or perturbing the central regions, though this process is subtler and less understood. Investigating correlations between shell presence and SMBH activity or mass offers another frontier for research. Another fascinating frontier is the relationship between shell galaxies and galactic feedback processes, the effects of energetic phenomena such as supernova explosions and active galactic nuclei on their host galaxies. Feedback can regulate star formation and drive gas outflows, influencing the gas content and structure of shells and their host galaxies. Understanding how feedback interacts with the merger-driven formation of shells informs broader models of galaxy self-regulation. On the observational front, the search for shell galaxies benefits tremendously from the development of wide-field, deep imaging surveys. Projects like the Sloan Digital Sky Survey (SDSS), PanSTARRS, and the Dark Energy Survey (DS) have revealed many new shell galaxies by capturing faint features over large areas of the sky. Upcoming surveys, such as the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, promise to revolutionize this field by detecting even fainter and more distant shells, enabling a comprehensive census. In addition to optical surveys, radio astronomy provides valuable insights. For instance, the presence and distribution of neutral hydrogen gas, HI, in shell galaxies can be mapped using radio telescopes. These observations reveal whether the mergers that created shells involve gas-rich satellites and how the gas interacts with the stellar shells. Such data help build a full multi-phase picture of galactic mergers, combining stars, gas, dust, and dark matter. The study of shell galaxies also resonates with the field of stellar population synthesis, the modeling of the integrated light from stars to infer their ages, metallicities, and formation histories. By applying sophisticated synthesis models to shell regions, astronomers extract detailed histories of the progenitor satellites and their contribution to the host galaxy's assembly. From a dynamical perspective, the orbits of stars and shells can be highly radial, leading to phase wrapping, a process where stars released during the merger phase align at similar points in their orbital paths, creating the visible shell edges. Over time, phase mixing gradually disperses the shells. Understanding this interplay between phase wrapping and mixing is key to interpreting the observed shell patterns and constraining merger timelines. The cultural and philosophical impact of shell galaxies should not be understated. These celestial phenomena embody the dynamic, evolving nature of the cosmos, reminding us that the universe is not a static backdrop but a living, breathing entity shaped by ongoing interactions. The shell's delicate arcs are cosmic echoes of collisions and mergers, testaments to the interconnectedness of matter across scales unimaginable to human experience. As we stand on the threshold of new observational capabilities and theoretical insights, the exploration of shell galaxies promises to remain a fertile ground for discovery. Each shell traced and analyzed brings us closer to unraveling the history of galaxies and the fundamental forces governing cosmic structure. In doing so, shell galaxies not only enrich our scientific understanding, but also inspire a profound appreciation for the beauty and complexity of the universe we inhabit. One cannot ignore the exciting potential of multi-messenger astronomy in advancing our understanding of shell galaxies. Traditionally, shell galaxies have been studied primarily through electromagnetic observations, visible light, infrared, radio waves, and X-rays. However, with the advent of gravitational wave astronomy, neutrino detectors, and cosmic ray observatories, new avenues open for investigating the dynamic processes that accompany galaxy mergers. Gravitational waves, ripples in space-time produced by massive accelerating objects, are expected to emanate not only from compact binary mergers, such as those involving black holes and neutron stars, but potentially also from the complex gravitational interactions during galaxy collisions. While the gravitational wave signals from shell-forming minor mergers are likely too faint for current detectors, future observatories, such as the Laser Interferometer Space Antenna, LISA, may detect signatures of massive black hole mergers within merging galaxies, events that sometimes accompany or follow the interactions that produce shells. Neutrino astronomy, though still in its infancy, offers prospects for revealing energetic processes within merging galaxies, such as bursts of star formation or supernova explosions triggered by merger-induced gas compression. These energetic events could correlate with the formation or evolution of shell structures, providing a complementary perspective on the life cycles of galaxies. Moreover, cosmic ray studies, through the detection of high-energy particles originating from galaxies, can shed light on energetic feedback mechanisms that regulate star formation and gas dynamics in shell galaxies. These mechanisms are crucial for understanding how mergers influence the interstellar medium, and consequently, the morphology and evolution of shells. Returning to the optical and near-infrared realms, adaptive optics and space-based telescopes allow astronomers to resolve fine details within shells, such as star clusters, young stellar populations, and subtle substructures. The Hubble Space Telescope has revealed intricate shell features and star formation knots, challenging previous assumptions that shells contain exclusively old stars. These findings hint at the possibility that shells can harbor complex stellar populations, including those formed during or after the merger events. The chemical composition of shell stars offers additional clues about their origins. By analyzing the spectra of shell stars, astronomers determine their metallicities, the abundance of elements heavier than hydrogen and helium, which reflect the star formation history of their progenitor galaxies. Variations in metallicity within shells can indicate the diversity of merging satellites, ranging from small dwarf galaxies with low metallicities to more massive, chemically enriched companions. In terms of environment, shell galaxies are often found in low-density regions, such as galaxy groups or the outskirts of clusters, where minor mergers are more common than disruptive major mergers typical of dense cluster cores. This environmental dependence helps astronomers understand how local cosmic neighborhoods influence galactic growth and transformation, emphasizing that galaxy evolution is not only a matter of intrinsic properties but also extrinsic circumstances. The identification and cataloging of shell galaxies also benefit from citizen science projects like Galaxy Zoo, where volunteers help classify galaxies in large datasets. Such collaborative efforts accelerate discoveries, uncover rare and peculiar shell galaxies, and enable statistical studies that reveal patterns and anomalies essential for theoretical modeling. Looking forward, the interplay between observations, simulations, and machine learning promises to revolutionize shell galaxy research. Artificial intelligence algorithms can sift through vast datasets, detect faint shell features, classify morphologies, and even predict merger histories, vastly increasing the efficiency and scope of discovery. In a broader philosophical context, the study of shell galaxies underscores a fundamental truth of the cosmos: change is the only constant. These ghostly arcs, fragile yet enduring, narrate stories of destruction and creation, of cosmic cannibalism that shapes the very structure of the universe. They remind us that galaxies are not isolated islands but participants in an ongoing cosmic web of interaction, growth, and transformation. As humanity's gaze extends ever deeper into the cosmos, shell galaxies will remain luminous signposts, guiding us through the complex narrative of cosmic evolution. They challenge us to refine our theories, innovate our technologies, and expand our imagination. In doing so, they enrich not only the science of astronomy, but the human spirit's quest to understand the universe and our place within it. Expanding further on the profound significance of shell galaxies, it's important to consider how these structures can also illuminate the timeline of cosmic events and serve as natural cosmic clocks. Because shells form from stars released during specific merger events, their spatial distribution and brightness profiles encode information about the time elapsed since the merger occurred. By modeling the dynamics of stars and shells and their gradual dispersion due to phase mixing, astronomers can estimate the age of shell structures, thus reconstructing the sequence of interactions a galaxy has experienced. These temporal constraints are crucial for understanding the episodic nature of galaxy growth. Instead of a smooth, continuous process, the assembly of galaxies often proceeds through discrete events separated by hundreds of millions or billions of years. Shell galaxies are direct witnesses to these episodic episodes, their delicate arcs fading with time and eventually dissolving into the galaxy's stellar halo. This fading makes the detection of shells in more distant, earlier epochs of the universe challenging but also scientifically valuable because observing shells at different cosmic times allows astronomers to chart the merger rate evolution. The connection between shell galaxies and the broader stellar halo populations around galaxies also merits attention. The stellar halo, an extended, diffuse component of stars surrounding the main body of a galaxy, often contains remnants of past accretions, including shells, streams, and other tidal features. By studying the overlap and distinctions between shells and halos, astronomers can unravel the layered history of accreted material and gain insights into the hierarchical nature of galaxy formation predicted by the lambda cold dark matter cosmological model. Interestingly, the prevalence and prominence of shells vary across different galaxy types and environments. For example, while many massive elliptical galaxies display pronounced shells, spiral galaxies tend to show fewer or less obvious shells, possibly because their disks are dynamically colder and more fragile, making them less likely to produce long-lasting shell features after minor mergers. However, some peculiar spiral galaxies with past merger activity do exhibit shell-like features, suggesting that shells may form under a wider range of conditions than previously thought. Delving into the future prospects for shell galaxy research, next-generation telescopes such as the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, will push observational boundaries, enabling the study of shells in much more distant galaxies. This will allow astronomers to probe the early universe's merger history directly and test theoretical predictions about the role of minor mergers in shaping galaxies soon after their formation. Additionally, the increasing resolution and sensitivity of instruments will permit detailed spectroscopy of shell stars, unveiling their individual motions and chemical fingerprints. This data will refine models of shell formation and galaxy assembly, potentially identifying variations in dark matter distributions and merger dynamics with unprecedented precision. From a computational perspective, advances in hydrodynamical simulations incorporating baryonic physics, such as gas cooling, star formation, and feedback, will produce more realistic models of shell galaxy formation. These simulations can capture the interplay between stars, gas, and dark matter during mergers, shedding light on how shells interact with other galactic components and evolve over time. Moreover, interdisciplinary approaches combining astrophysics with data science, statistical methods, and machine learning will enable the extraction of subtle shell features from noisy data, classification of shell morphologies at large scale, and predictive modeling of merger histories. Shell galaxies represent not only a captivating cosmic phenomenon but a vital key to understanding the grand narrative of galaxy evolution. Their study bridges scales from individual stars to dark matter halos and spans epochs from the nearby universe to cosmic dawn. As we continue to unveil the secrets encoded in these ghostly structures, we enrich our comprehension of the dynamic, ever-changing cosmos and reaffirm the interconnectedness of all cosmic matter. The shells whisper stories billions of years old, stories of cosmic collisions, growth, and transformation that resonate across space and time. They remind us that the universe is a tapestry woven from countless encounters, and that even the most serene and elegant structures carry within them the marks of a tumultuous past. With every new discovery, shell galaxies beckon us to look deeper, think broader, and appreciate the cosmic dance that shapes the galaxies, stars, and ultimately, ourselves. As our journey through the enigmatic realm of shell galaxies continues, it's worth contemplating the aesthetic and symbolic power these formations exert, not only on astronomers but on anyone who gazes upon them. Shell galaxies are visual poetry written in stars. They embody the paradox of fragility and permanence, faint, ephemeral arcs that persist for hundreds of millions of years, testifying to ancient violence wrapped in silence and beauty. Their forms seem almost sculptural, natural mandalas that arise not from deliberate design but from gravitational inevitability. These galaxies also underscore the importance of visual interpretation in astronomy. Many shell structures were first discovered by accident or through careful scrutiny of images, sometimes by professional astronomers and other times by amateur skywatchers. This highlights an essential aspect of astronomy as both an analytical science and a deeply visual discipline. We rely on patterns, shapes, and brightness contrasts to interpret phenomena at incomprehensible scales, and shell galaxies are among the most graceful signatures of these cosmic processes. And then there's the symbolism of shells themselves. In art, architecture, and nature, shells are often associated with layers, memory, and growth. The nautilus shell, for instance, is a symbol of expansion and order emerging from chaos. Likewise, shell galaxies visually encode memory. Each ripple or arc an echo of an encounter, a ripple in space-time caused by a cosmic meeting. In this way, shell galaxies can be seen as archives of cosmic history, frozen in elegant arcs. Turning back to the physics, there's also fascinating research into the orbital structure of shell stars. Most shell galaxies are modeled under the assumption that the stars forming the shells are on nearly radial orbits. However, newer simulations suggest that depending on the specific dynamics of the merger and the potential well of the host galaxy, stars in the shells may exhibit more complex orbital distributions. This could lead to layered shells that cross and interfere, or shells that evolve into other types of stellar substructure over time. Moreover, the symmetry of shells, often appearing as concentric arcs centered around the galaxy's core, belies a complex dynamical origin. In some cases, these arcs are aligned with the galaxy's major axis. In others, they appear skewed or warped. These variations can inform us about the angular momentum of the merger, the inclination of the orbit, and even possible perturbations from other nearby galaxies. Understanding these subtleties allows astronomers to reverse engineer the dance of two galaxies, decoding trajectories and impact parameters from the resulting patterns in the stars. Additionally, research into shell galaxies with active galactic nuclei, AGN, has revealed that some host galaxies show signs of central black hole activity, likely triggered or enhanced by the same merger events that created the shells. While minor mergers are less violent than major ones, they can still deliver enough material to feed a central black hole, or at least disturb gas reservoirs enough to trigger new cycles of accretion and feedback. This coupling of shell formation with AGN ignition provides insight into the coevolution of galaxies and their central engines. It is also fascinating that some shell galaxies show asymmetrical brightness among shells on opposite sides of the galaxy. These brightness imbalances may reflect the mass distribution of the infalling satellite or the density of the dark matter halo. In other cases, they may be the result of a secondary encounter with the same satellite in a bound orbit, each pass producing a new generation of shells. This possibility points to recurrent shell formation, where a single minor merger doesn't just leave behind one set of shells but a sequence of them over time. In this way, a galaxy can wear multiple layers of shells, like rings of a tree trunk, each layer marking a separate pass of the same cosmic intruder. This metaphor adds a rich chronological dimension to shell galaxies, making them not just archives of a single event but potentially palimpsests of repeated gravitational interactions, each written atop the last. Some researchers have even proposed using shell kinematics as a probe for alternative theories of gravity, such as modified Newtonian dynamics, MOND, as the behavior of stars at large radii in galaxies, where shells often appear, could help distinguish between dark matter frameworks and modifications to gravity. The shapes, densities, and motions of shell stars become a testing ground for our most fundamental understanding of the universe. In this light, shell galaxies are not just observational curiosities. They are laboratories of cosmic physics, bridges between theory and observation, and touch points for debates about the very fabric of space and time. They straddle the disciplines of cosmology, galactic dynamics, stellar evolution, and astrophysical imaging. And yet, in the grand catalogue of the cosmos, shell galaxies remain a minority, rare, ghost-like, fleeting. Perhaps that is part of their allure. Like cosmic fossils, they preserve a fleeting moment in a galaxy's life, and catching sight of them feels like witnessing something almost sacred, the silent aftermath of a cosmic dance. With future technologies, deeper surveys, and more refined simulations, the number of known shell galaxies will surely grow. But even as they become more numerous, each will remain unique, shaped by the specific circumstances of its creation. The symmetry, curvature, sharpness, and brightness of each shell system will tell a slightly different story about galactic encounters, star formation, black hole growth, and the shape of invisible halos. In pursuing these stories, we are not only charting the structure of galaxies, we are reading the universe's autobiography, one arc at a time. In continuing to peel back the layers of meaning and science behind shell galaxies, we are confronted with a realization that touches the very essence of cosmic evolution. Shell galaxies are evidence of the universe's memory. Galaxies, often perceived as eternal and immutable in their elegance, are in fact shaped by cataclysmic interactions, each leaving behind imprints, some sharp and dramatic, others subtle and haunting. Shells are these imprints. They are the fossilized shockwaves of a merger, lingering long after the violence has passed, much like tree rings after a storm year, or the ripples left on a pond's surface long after the stone has sunk. This metaphor of memory extends beyond poetic interpretation and into actual observational methodology. Through stellar population synthesis models, astronomers can estimate the ages of shell stars, their formation epochs, and the starburst activity that accompanied their arrival. These age estimates, combined with the shell radii and spacing, enable researchers to estimate merger chronologies, effectively creating a timeline for the galaxy's transformation. Moreover, the angular distribution of shells around their host galaxies, whether they appear in bisymmetric patterns, interleaved arcs, or random scattering, can yield insights into the orbital plane of the merger and whether the event involved a head-on plunge, a tangential skim, or a looping decay. In this way, astronomers treat each shell galaxy like a crime scene, reconstructing the movements, mass, and orientation of the infalling satellite long after it has been digested and absorbed. In certain cases, high-resolution imaging has revealed nested shells, concentric arcs stacked like translucent layers. These patterns suggest that the merger event was gradual, with the disrupted satellite galaxy shedding its stars in successive episodes, each round of debris settling into the host galaxy's potential well and forming a new shell. Such galaxies are especially rich in dynamical complexity and serve as some of the best testing grounds for n-body simulations of galactic interactions. The orbital decay of the intruding galaxy due to dynamical friction, the process by which the satellite slows down as it transfers energy to the stars and dark matter of the larger host, plays a crucial role in determining the final distribution of shells. The speed and angle of this decay affect how the satellite's mass is stripped and at what distances the shell stars will appear. Dynamical friction itself is tied to the dark matter halo surrounding the host galaxy, meaning that every shell system is also, indirectly, a probe of the invisible architecture that governs galactic motion. This brings us to a fascinating point: shell galaxies as indirect maps of dark matter. Because the stars in the shells respond to the overall gravitational potential, their spacing and symmetry encode information about the shape, extent, and concentration of the host's dark matter halo. While dark matter remains undetectable by direct electromagnetic means, it reveals its presence through its influence on visible matter. Thus, shell galaxies offer a kind of gravitational cartography, stars moving along orbits dictated not only by luminous mass but also by the mysterious substance that constitutes most of the galaxy's actual mass. And yet, despite this immense potential, shell galaxies remain elusive and often underrepresented in galactic catalogs. Their low surface brightness makes them extremely difficult to detect, especially at cosmological distances. Many of the known shell galaxies were discovered through deep imaging surveys or targeted long-exposure observations, such as those from the MATLAS, Mass Assembly of Early Type Galaxies with Their Fine Structures, survey, which uses advanced processing techniques to uncover faint galactic structures. Without such careful treatment, many shell systems remain hidden in plain sight, buried under the noise of sky glow, foreground stars, and instrument limitations. This is where next-generation survey missions like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will play a transformative role. By scanning large portions of the sky with unprecedented depth and frequency, LSST is expected to uncover a vast population of low-surface brightness features, including thousands of previously unseen shell galaxies. These discoveries will revolutionize our statistical understanding of minor mergers and allow for comparative studies across galactic environments, masses, and evolutionary states. In the computational realm, increasingly sophisticated machine learning techniques are being trained to recognize faint shells and classify them automatically. Convolutional neural networks, for example, can be taught to detect arcs and ripples that human eyes might miss in noisy datasets. These tools are already being deployed to comb through archival data from SDSS, Sloan Digital Sky Survey, Hubble, and other missions, uncovering hidden galaxies that bear the faint scars of ancient mergers. Furthermore, ultraviolet and infrared observations have begun to expand our knowledge of shell galaxies into other wavelengths. While optical light is most effective at revealing shell morphology, infrared allows astronomers to peer through dust and view older, redder stars, while UV can highlight younger, hot stars that may have formed in shell-triggered starbursts. This multi-wavelength approach paints a fuller portrait of shell systems, capturing not just their skeletons, but their history of gas, dust, and stellar birth. What emerges from this growing body of knowledge is a picture of shell galaxies not as isolated oddities but as crucial waypoints in the story of galactic evolution. Their presence marks a turning point in a galaxy's life, moments when external influence reshaped internal structure, when old stars were flung into new orbits, when black holes were nudged awake, and when once separate galaxies merged to form a single, restructured whole. These moments echo throughout the galaxy structure for billions of years, gradually fading but never truly gone. Like the ruins of ancient civilizations on Earth, the shells of galaxies tell of a past defined by motion, collision, and transformation. And like archaeologists uncovering buried cities, astronomers sift through these stellar remains to reconstruct a universe in motion. The fact that galaxies can wear these memories as visible ornaments in the sky, ornaments we can see from millions of light years away, is both a triumph of physics and a humbling reminder of our place in the cosmos. When we look at shell galaxies, we are not just studying astrophysics, we are witnessing time made visible. The stars themselves trace the orbits of forgotten galaxies. The shells are like ghost trails on a canvas of space-time. And that, perhaps, is the deepest mystery of all, that the universe remembers, and it remembers in light. As we delve even deeper into the realm of shell galaxies, their implications begin to extend beyond astrophysical curiosity. They challenge our very understanding of cosmic structure and temporal permanence. When we observe these shells, some stretching over hundreds of thousands of light years, we are witnessing a process of celestial storytelling, where every arc is a sentence in the biography of a galaxy. It's crucial to recognize that shell galaxies serve as a transitional phase in the morphological evolution of galaxies. For instance, a galaxy that begins as a relatively quiescent elliptical may pass through a shell-rich phase after merging with a smaller companion, later settling into a more stable, shell-less appearance. Alternatively, some disk galaxies might momentarily display faint shell-like features if a minor merger deposits stars into extended orbits. This transient nature suggests that many more galaxies may have once been shell galaxies but have since lost their structures to the slow, inexorable process of dynamical relaxation. Shells, therefore, are not eternal. They are impermanent features that tell us when, not just where, a galaxy has changed. Over time, the coherent structure of shells becomes blurred. Stars once aligned in sharp arcs diffuse into the larger stellar halo. As this happens, the galaxy loses its visible merger scars and becomes a more homogeneous system. This transformation represents a key step in the galactic aging process, where once active and disruptive events slowly fade into the background, leaving behind only the whisper of their presence in velocity dispersion or metallicity gradients. What's fascinating is that shell galaxies don't just provide insight into past events, they are predictive tools as well. By studying the dynamical state and distribution of shells, astrophysicists can model a galaxy's future evolution. Will it develop into a larger elliptical? Will it undergo additional mergers? Will the presence of remaining substructures catalyze further star formation or black hole activity? Each of these scenarios depends on clues hidden within the arcs themselves. We must also consider the cosmic environment in which shell galaxies live. Shells are more commonly found in relatively isolated galaxies or in low-density environments like galaxy groups rather than rich clusters. In clusters, frequent high-speed interactions often disrupt the formation or longevity of shell structures. In contrast, galaxies in sparse environments have more time and space to develop well-defined shells from slow, radial mergers. This environmental dependence suggests that shell galaxies can be used as tracers of the broader large-scale structure of the universe, offering clues about how galaxies and dark matter halos are distributed on cosmic scales. In recent years, astronomers have explored the potential of polar shell galaxies, in which the shells are not aligned along the major axis of the host galaxy but rather form in polar configurations. These are thought to arise from more complex merger geometries, such as satellites entering on inclined orbits, and may tell us about anisotropies in the galactic gravitational field or non-spherical shapes of dark matter halos. Polar shells challenge traditional models and demand three-dimensional simulations that go beyond simple radial infall scenarios. There's also growing evidence that gas-rich shell galaxies may experience induced star formation as a result of merger-driven compression of gas. This results in shell-induced starbursts, where young, blue stars appear along the arcs, essentially lighting up the gravitational structure like a cosmic neon sign. These star-forming shells are rarer than purely stellar ones but offer a dual insight into both the dynamics and chemistry of merger processes. Chemical analysis of shell stars can reveal whether they originated from the satellite galaxy or were drawn out of the host itself during tidal interactions. Stars that differ significantly in metallicity from the host galaxy's population often point to external origins. In this way, metallicity gradients across shells act as galactic fingerprints, providing a forensic method for distinguishing endogenous versus exogenous components. This leads us into the realm of stellar archaeology, where shell galaxies become dig sites for understanding galaxy assembly. By piecing together the motion, age, and chemical composition of shell stars, astronomers can reconstruct the lost galaxy from which they came, its mass, orbital trajectory, and eventual demise. Such reconstructions are not only scientifically impressive but deeply poetic, We are bringing back to life a galaxy that died billions of years ago, its memory preserved only in the orbiting ghosts of its stars. Another fascinating area is the potential link between shell galaxies and galactic nuclei activity. While major mergers are often credited with feeding central supermassive black holes, even minor mergers, such as those responsible for shell structures, can funnel material inward via tidal torques. This means that some shell galaxies may have flickering AGNs or weak radio and X-ray emissions tied to merger events. Thus, even the faintest of arcs might imply a turbulent past not only for the galaxy's outskirts but for its very core. Let's also not forget the aesthetic dimension of shell galaxies. Their beauty, symmetry, and rarity make them favorites among deep sky observers and astrophotographers. Amateur astronomers with high-quality CCD setups and long exposure times have captured remarkable images of these faint features, often revealing structures unseen in large survey data. These images don't just enrich scientific understanding, they inspire wonder and connect the public with the grandeur of cosmic evolution. In the context of public science education, shell galaxies serve as excellent metaphors. Teachers and communicators often use them to illustrate ideas like gravitational interaction, orbital motion, galactic cannibalism, and time evolution. They are visual, intuitive, and dramatic. Their arcs convey motion and force in ways that spreadsheets of data or mathematical equations cannot. In this sense, shell galaxies are ambassadors of the cosmos, inviting audiences into the deeper mysteries of structure formation. As our understanding of shell galaxies grows, so too does our realization of how delicately balanced the universe must be for such structures to form and persist. The right mass ratios, orbital parameters, gas content, and dark matter distribution must align perfectly to produce shells visible for hundreds of millions of years. Each shell galaxy, then, is a kind of cosmic coincidence, a product of timing, motion, and gravity playing out on galactic scales. Ultimately, shell galaxies remind us that the universe is not static but dynamic, not peaceful but shaped by the echoes of ancient violence. They show us that galaxies are not isolated islands but social beings, colliding, merging, consuming, and reshaping each other over time. They show that beauty can arise from destruction, that structure emerges from chaos, and that even the faintest arc of starlight carries the memory of a galaxy that once was. And in their slow fading into the background of the universe, shell galaxies also remind us of something profoundly human, that nothing lasts forever, but everything leaves a trace. As we push further into the mystery of shell galaxies, we encounter a broader philosophical question hidden beneath the science. What does it mean for galaxies to remember? Shells are not just remnants of cosmic events, they are evidence that the universe itself has a kind of structural memory. In the language of general relativity and astrophysics, this memory is not conscious, of course, but encoded in mass, motion, and light. The shells are the residual notes of a galactic symphony, echoing long after the instruments have fallen silent. Let's now explore how shell galaxies could be vital benchmarks for refining cosmological simulations. In the large-scale computational models that simulate structure formation in the universe, like the Millennium Simulation or Illustris TNG, galaxies are born, merge, evolve, and interact over billions of years. But verifying whether these simulations accurately reflect reality depends on finding observable markers of past events. Shell galaxies provide one of the most distinct and delicate such markers. Because they are fragile, low-surface brightness features, their formation and persistence in simulations demand a high degree of resolution. If a simulation can reproduce shells with correct radial spacing, morphology, and longevity, it's a sign that it accurately models gravitational dynamics, dynamical friction, mass stripping, and orbital evolution. That's why shell galaxies have become validation targets for cutting-edge cosmological models, used not just to describe the past but to predict the future. Simulations also allow us to explore scenarios we cannot easily observe in real time. For example, by modeling galaxies with different types of dark matter, cold, warm, or even self-interacting, we can ask, how does the nature of dark matter affect the formation and appearance of shell galaxies? Some findings suggest that more diffuse or less interactive dark matter results in more smeared-out shell features, while denser, more clumpy halos lead to sharper, more nested arcs. If these differences can be correlated with real observations, shell galaxies could become tools for testing dark matter models, which remains one of the greatest challenges in physics. Now let's consider an exciting frontier: shell galaxies at higher redshifts. Most of our current observations focus on relatively nearby galaxies, within 200 million light-years, because detecting shells at greater distances is incredibly difficult. But with upcoming observatories like the Nancy Grace Roman Space Telescope and the James Webb Space Telescope, JWST, we are poised to look further into the past with much greater resolution and sensitivity. Detecting shells in galaxies that existed several billion years ago would allow us to chart how frequent such minor mergers were in earlier epochs, and whether their frequency and morphology evolved with cosmic time. In essence, we'd be looking at the youth of shell galaxies, observing them when the universe was denser, more turbulent, and more merger-prone. We may find that what we currently see as rare and delicate phenomena were once far more common in the chaotic early cosmos, ghostly signatures written across a more active and formative sky. Meanwhile, the concept of multiphase shell formation has added complexity to our models. In this view, a galaxy doesn't acquire all its shells in a single event, but in multiple successive merger episodes. Each wave of infalling satellite stars creates its own set of shells. Some of these may overlap, while others remain distinct, forming a layer cake of arcs, each marking a different time in the host galaxy's history. This overlapping structure may be spectroscopically disentangled, with each set of shells possessing different stellar populations, motions, and chemical signatures, like tree rings that represent different seasons. Spectroscopy also opens the door to understanding the kinematics of shell stars. By measuring their radial velocities, astronomers can trace whether the stars are moving outward, inward, or orbiting in elliptical paths. These motion patterns directly relate to the type of gravitational potential governing the host galaxy, and by extension, the mass distribution of both visible and invisible matter. In some well-studied cases, such as the elliptical galaxy NGC 3923, careful spectroscopic mapping of shell velocities has allowed for detailed modeling of the underlying potential well. There's also growing interest in comparing shell galaxies to other types of fine structure seen in galaxies, such as tidal tails, plumes, bridges, and streams. All of these are signs of past interactions, but shells are uniquely symmetric and radial, forming as a result of phase-wrapped stellar debris. Tidal tails, by contrast, are more prominent in gas-rich disk galaxy interactions, often resulting from angular momentum transfer rather than radial infall. This difference highlights the importance of orbital geometry. The shell-making process is sensitive to a satellite galaxy's infall trajectory, particularly the angle and eccentricity of its orbit. Near-radial orbits are most conducive to shell formation because they allow the satellite stars to plunge deeply into the host galaxy and then fan out in radial orbits. In simulations, a satellite on a non-radial, high angular momentum orbit tends to produce asymmetric features or no shells at all. Therefore, the presence of shells suggests a dynamically cold merger, a relatively slow, direct collision rather than a glancing encounter. This has important implications for the frequency of shell galaxies in different cosmological environments. For example, radial mergers are more likely in low-density cosmic voids or filaments, where galaxies drift more freely, than in crowded clusters, where chaotic gravitational tugs prevent such orderly collisions. Hence, by mapping shell galaxies across the cosmic web, we might gain insight into how the geometry of the universe itself influences galaxy evolution. Let us not forget the role of galactic morphology. While shell structures are most often found in elliptical galaxies, they are occasionally seen in lenticular and even spiral galaxies, challenging the notion that shells are strictly post-merger ellipticals. When found in disk galaxies, shells usually appear fainter and more distorted, possibly due to the competing influence of disk rotation. These rare systems suggest that even delicate structures like spiral arms can coexist with radial debris arcs, at least for a time. These rare spiral shell hybrids offer valuable information about disk survival after minor mergers. In some cases, the infalling satellite is not massive enough to destroy the disk completely, yet strong enough to generate radial oscillations in the stellar population. This creates shells superimposed on rotating disk components, a complex dynamical system that tests the limits of current models. As the catalog of known shell galaxies grows, so too does the possibility of finding anomalies, shell galaxies that defy expectations. Some possess shells that appear too thick, too irregular, or too widely spaced. Others show unusual alignments or asymmetries. These outliers often prompt refinements to existing models or suggest that unknown variables, like triaxial dark matter halos or past flyby events, may play a role. Such exceptions are not failures of science, they are its cutting edge. They remind us that every rule has exceptions and that every structure we observe might hint at a deeper principle yet to be discovered. The future of shell galaxy research will be shaped by three key developments: deep sky surveys, AI-powered pattern recognition, and high-resolution spectroscopic mapping. As we combine these tools, the faint echoes of ancient mergers will become louder, clearer, and more revealing. What was once hidden in the shadows will take center stage. And as we continue our search for meaning in these cosmic arcs, we are reminded that the universe is not just expanding in space. It is expanding in story, each shell a new chapter, each galaxy a different narrative of time, force, and form. This journey through the realm of shell galaxies, though grounded in science, also borders on something more profound, a reflection of time itself etched into the cosmos. When we peer into the arcs of starlight that wrap around the galaxy's luminous heart, we are not merely observing a structure. We are reading a cosmic ledger, where each shell is a timestamp, each ripple a relic of transformation, and each void between arcs a pause in the rhythm of a universal waltz. It is in this rhythm that we find not only the past preserved but also the clues to the unseen mechanics of the universe. As our observations grow increasingly precise, attention has also turned to the faintest, outermost shells, those barely distinguishable from the background of intergalactic space. These outer shells often extend hundreds of thousands of light-years from the galactic core, making them among the largest known stellar structures associated with any one galaxy. They also tend to be the oldest, having originated from the first passages of the merging satellite. Because these stars have had the most time to travel outward, their positions are highly sensitive to the total gravitational potential of the galaxy and its surrounding dark matter halo. This has opened a powerful new avenue for research, using the radial extent of outer shells as tracers of halo mass and shape. If the gravitational potential is shallow, stars can travel further before slowing down. If it's steep, they remain more confined. In practice, comparing shell locations with predictions from dark matter models allows astrophysicists to estimate not only the total mass of the galaxy, including its dark component, but also the geometry of that mass, whether it's spherical, oblate, or triaxial. Moreover, variations in shell brightness can inform us about stellar density distributions. If a shell is more prominent on one side than the other, it may indicate an uneven influx of stellar material or a non-uniform potential, possibly influenced by prior interactions, or even the presence of a nearby satellite that perturbs the symmetry. Such deviations provide astronomers with dynamical clues to past interactions and internal galaxy structure. One exciting tool in this investigation is the use of integral field spectroscopy, which allows scientists to map not just the velocity of stars in a shell but their metallicity, age, and motion simultaneously. With this method, we can isolate different shell systems within the same galaxy, identify which arcs belong to which infalling satellites, and date those events with remarkable accuracy. This turns shell galaxies into cosmic time machines, letting us rewind the history of stellar collisions over billions of years. There is also increasing interest in understanding the life cycle of shell systems, how they form, persist, and eventually fade. Some simulations suggest that the lifespan of well-defined shells may be only 1 to 2 billion years before they blur into the galactic halo. However, others propose that under certain conditions, especially in massive, slow-evolving galaxies, shells might remain coherent for far longer. Factors such as orbital precession, dynamical friction, and the presence of dark matter subhalos can either stabilize or disrupt these structures. This makes the study of fading shells an important subfield in understanding galactic longevity. Fading shells also connect to the phenomenon of stellar halos, vast, diffuse populations of stars that surround most large galaxies. Some researchers argue that the outer regions of stellar halos are fossilized shell systems, smoothed over by time but still carrying the kinematic and chemical imprint of past mergers. By disentangling this fossil record, we might be able to reconstruct not just single merger events, but the entire assembly history of a galaxy over cosmic time. Let's not overlook the implications for stellar populations. The stars that comprise shells can be used to probe the stellar initial mass function, IMF, of the accreted galaxies, especially if they come from systems that were chemically distinct. This allows for a test of whether dwarf galaxies, the usual progenitors of shell systems, followed the same IMF as larger galaxies, a key question in understanding star formation across different environments and epochs. The presence of globular clusters within shells adds another dimension. In some galaxies, globular clusters, dense groups of ancient stars, are found distributed along shell features, suggesting that these clusters too may have been accreted during minor mergers. By mapping their distribution, we can identify the likely trajectories and origins of past satellite systems, turning globulars into dynamical tracers of galactic evolution. There's even the possibility that some ultra-diffuse galaxies, those ghostly, low-density systems observed in clusters, may have once been part of shell-forming mergers. Their apparent absence of central structure and dispersed appearance could be the aftermath of tidal disruption, with some of their stars now residing in faint shells around a more massive neighbor. If so, this would provide crucial data for modeling galactic recycling, where small galaxies are consumed and their components repurposed into larger systems. In the observational frontier, space telescopes and deep sky surveys continue to uncover new shell systems, some in unexpected places. Pan-STARRS, Dark Energy Survey, and especially the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, are expected to find thousands of new shell galaxies, increasing our catalog exponentially. With this data, we will finally be able to answer statistical questions that have long eluded researchers. How common are shells? How do they correlate with galaxy type, environment, or cosmic epoch? What does their distribution tell us about the hierarchical model of galaxy formation? Each discovery will add another data point in our pursuit of a unified theory of galactic interaction, where tidal debris, shells, and stellar streams are understood not as isolated curiosities but as integral features of cosmic structure building. In addition to their scientific value, shell galaxies continue to inspire art, imagination, and public fascination. The graceful curves, the ethereal glow, the narrative potential, they are natural visual metaphors for memory, loss, and renewal. Just as a seashell holds the shape of an ocean wave long after the tide has receded, these galaxies hold the form of cosmic events long past. They are scars in the sky that do not disfigure, but rather elevate, reminding us that even destruction can give rise to elegance. So when you next look at an image of a shell galaxy, perhaps NGC 474 with its swirling spirals of faint light, or NGC 3923 with its concentric ripples of stellar haze, pause and remember, you are witnessing a story that began billions of years ago, with the fall of one galaxy into another. A story still unfolding, in arcs of light and gravity, at scales almost beyond comprehension. And though the stars in those shells will one day disperse, their legacy will remain, in the models they inspire, the discoveries they prompt, and the questions they raise. Shell galaxies are not just the aftermath of collisions. They are monuments to transformation in the universe, a delicate balance of violence and beauty, chaos and order, impermanence and cosmic memory. As we continue to delve into the mystery and majesty of shell galaxies, a subtle but vital question emerges. What role do these galactic fossils play in the grand architecture of the cosmos? They are not merely remnants of past collisions, nor just beautiful anomalies. They may, in fact, be crucial signposts, pointing the way to deeper truths about the structure, origin, and destiny of matter on the largest scales. Let's return for a moment to a central concept that underlies much of galaxy evolution: hierarchical formation. In this framework, the universe didn't start with giant galaxies. It began with small, clumpy structures that merged over time to create larger and more complex systems. Shell galaxies are perhaps the clearest observational proof that this process didn't end billions of years ago. It's still happening. They are snapshots of this cosmic growth in action, direct evidence that galaxies are still cannibalizing their smaller neighbors. But shell galaxies do more than just confirm hierarchical growth. Because they are highly sensitive to initial conditions, like satellite mass, orbit, timing, and impact angle, they serve as natural laboratories for testing cosmological models at an exquisite level of detail. Each shell is a fingerprint, and by decoding that print, astronomers can reverse engineer not just the collision that created it, but the larger galactic ecosystem in which it occurred. This makes shell galaxies indispensable for understanding galaxy assembly bias, the idea that a galaxy's properties depend not just on its mass, but on its history, when and how it assembled. Two galaxies of equal mass might look quite different if one underwent multiple minor mergers, evidenced by shells, while the other grew more quiescently. Such distinctions help explain the rich diversity we observe in galactic forms, colors, and stellar populations. This opens a tantalizing possibility. Could shells encode the biography of a galaxy? Might their number, spacing, symmetry, and composition tell us not only that a merger occurred, but when, how many times, and from what direction? If so, shell galaxies could become the Rosetta Stones of galaxy formation, giving astronomers a readable record of the long-forgotten past. There's also growing evidence that shell galaxies are not entirely passive actors in their story. The mergers that produce shells can also reignite star formation, either by delivering fresh gas or by compressing existing gas into new star-forming regions. This contradicts the idea that elliptical galaxies, the most common hosts of shells, are dead. In fact, some shell galaxies show ultraviolet and infrared evidence of recent starbursts, often concentrated near the nucleus, possibly triggered by the merging event itself. This dynamic interplay between past destruction and new creation hints at a deeper truth: the cosmos is not static. Even structures that appear serene and settled are still being shaped by invisible hands, gravity, momentum, and time. Shells are not just scars, they are also bridges, connecting the ancient past with an unfolding future. Another important question in modern astrophysics is the behavior of supermassive black holes, SMBHs, during mergers. When two galaxies collide, their central black holes will eventually spiral toward one another, potentially merging in a cataclysmic event that sends ripples through spacetime, gravitational waves. But long before this final coalescence, the dynamics of the host galaxies are disturbed. In shell galaxies, the stellar debris patterns might indirectly reflect the gravitational influence of dual SMBHs or off-center black holes. In some simulations, the recoil of a newly merged black hole, due to gravitational wave emission, can displace it from the galactic center. This might lead to asymmetric shells or even offset central features. Observing such anomalies could offer rare clues to these hidden processes, helping us link visible structures to invisible events. Similarly, researchers are investigating whether nuclear star clusters, often found in the cores of shell galaxies, may also be influenced by these complex dynamics. The infalling material from a satellite galaxy could either feed or perturb these central clusters, leading to starbursts, changes in chemical composition, or even cluster disruption. As more shell galaxies are observed with high-resolution spectroscopy and multi-wavelength imaging, astronomers hope to determine whether there are any correlations between shell systems and nuclear activity. Could a recent shell-producing merger be the spark that ignites an active galactic nucleus, AGN? Some studies suggest yes, pointing to a subset of shell galaxies that host weak AGNs, perhaps a sign that fresh material has recently reached the galactic core. This is particularly exciting because it links large-scale dynamics, like mergers and shell formation, to small-scale phenomena like accretion disks, jet formation, and SMBH feeding cycles. It underscores the interconnectedness of all galactic processes, from the outermost halo to the innermost event horizon. The role of shell galaxies in galaxy environment studies is also gaining attention. Researchers are now examining how the cosmic neighborhood, whether a galaxy resides in a dense cluster, a sparse void, or a filament, affects the formation and preservation of shells. In dense environments, frequent high-speed encounters may disrupt or blur shells. In quieter regions, they can persist longer and form more cleanly. Mapping this relationship could turn shell galaxies into environmental indicators, allowing astronomers to probe the ecology of the universe through these fragile signatures. Finally, we must return to the aesthetic and philosophical impact of shell galaxies. For decades, astronomers saw them as oddities, outliers, curiosities. But as the field matured, it became clear that these galaxies are not rare exceptions. They are an expected consequence of universal principles: gravity, momentum, energy conservation, acting over vast timescales. In this sense, shell galaxies are inevitable, just as ocean waves are inevitable when wind crosses the water. They are the most delicate expression of a violent process, proof that even in destruction, nature creates beauty. They remind us that the universe is not random, but structured, governed by laws that produce both chaos and elegance in equal measure. And so we end not with a final answer, but with an invitation to look deeper, to simulate better, to map wider, and to ask bolder questions. Because for every shell galaxy we discover, a new mystery is born. And for every ripple of light that arcs through the dark, there is a story waiting to be told, written not in words but in stars. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.